In the vast expanses of the universe, numerous celestial bodies exhibit extraordinary characteristics, making them exceptional even by space standards. Among these are exoplanets with striking similarities to Earth and others that have never experienced sunlight, residing in perpetually stormy conditions. Some planets are dominated by vast oceans with glowing ice blocks at their bottoms. Meanwhile, giant stars within multicolored nebulas can engulf entire planetary systems, and jellyfish galaxies with shining stellar tentacles span millions of light years. Embark with us on a fantastic journey to explore the most incredible cosmic wonders. Before venturing beyond our solar system, selecting a planet similar to Earth requires careful consideration of specific parameters. Scientists have developed the Earth Similarity Index, ESI, as a criterion based on a planet's radius, density, and average surface temperature. This index aids in estimating mass, chemical composition, gravitational levels, the presence of an atmosphere, and the likelihood of liquid water. The standard ESI is set with Earth's parameters as ideal, assigned a value of 1. Objects with an ESI under 0.5 typically include gas giants, extremely hot or cold celestial bodies, and most solar system planets. Even if a planet's radius and mass closely match Earth's, factors like proximity to the Sun or a dense atmosphere can render it unsuitable for life. Planets with ESI between 0.5 and 0.7 constitute the second category, offering more Earth-like conditions. However, a high ESI doesn't guarantee favorable conditions, as low-mass planets may lack a dense atmosphere or sufficient protection from radiation. The third category includes celestial bodies with ESI over 0.7, primarily exoplanets beyond our solar system. One notable exoplanet, Teegarden b, lies 12.5 light-years away from Earth. Orbiting a red dwarf star called Teegarden, it is part of a system discovered in 2003. Teegarden's star is a small red dwarf, emitting only 1,370 times less light than the Sun. The star's habitable zone is narrow, making conditions suitable for life challenging. Teegarden b has an ESI of 0.95, making it the most Earth-like exoplanet discovered. While its surface temperature is approximately -47 degrees Celsius on average due to the star's low luminosity, the potential existence of oceans beneath a layer of ice remains a possibility. Another intriguing celestial body in Teegarden's system is Teegarden c, which lies beyond the star's habitable zone. With an orbit completed in 11.5 days, Teegarden c is presumed to be a rocky planet with conditions less conducive to life. Despite Teegarden b's extreme proximity to its parent star, it exhibits Earth-like characteristics, such as a circular orbit and proximity to the habitable zone. Mathematical modeling suggests favorable conditions for liquid water and potentially habitable temperatures. Teegarden b is presumed to have a composition similar to Earth, with a massive metallic core, a silicate mantle, and a solidified rock crust. Its gravitational values closely resemble Earth's, and the planet's temperature profile supports the presence of liquid water. Despite its favorable parameters, challenges arise from potential temperature extremes due to its one-sided facing of the star and the red dwarf's tendency to flare up suddenly. However, the adaptability and resilience of biological organisms may offer possibilities for life. While Teegarden b appears promising, it is not flawless, and caution is warranted. Fluctuations in the red dwarf's luminosity and the planet's proximity to its star may impact its habitability. Nevertheless, the exploration of such celestial wonders enriches our understanding of the cosmos and fuels the ongoing quest for potential life beyond our solar system. In the vastness of the universe, cosmic fluctuations present the potential for celestial bodies to absorb cosmic radiation, while their currents may dissipate temperature variations. Over time, these conditions create an environment where primitive organisms could evolve in the warm depths, saturated with energy and microelements. Sometimes, even the smallest chance is sufficient for life to develop into something more complex. Typically, it is the potentially habitable planets with favorable conditions and a moderate climate that draw particular attention amid the vast diversity of worlds. Conversely, extremely dangerous objects stand out among others, forming a third category of anomalous celestial objects that exhibit unusual behavior. challenging our scientific understanding and warranting special attention. In the year 2009, within the environs of the Kepler 413 system, an unknown object passed between Earth and a distant star, momentarily reducing its luminosity. Initially perceived as a standard exoplanet transit, the discovery of a new celestial body was announced through high-precision calculations that allowed the determination of its parameters. This object, named Kepler 413 bits, revealed itself to be a cool giant with a mass approximately 25 times that of Earth and a radius around 40% that of Jupiter. However, 180 days later, an expected transit did not occur, and the planet seemingly vanished without a trace. Various hypotheses, such as a dark spot in the star's photosphere or a giant dust cloud, were initially considered. However, 800 days later, the mysterious object reappeared, revealing an unusually eccentric orbit influenced by gravitational perturbations from nearby binary stars. Kepler 413 bits' orbit oscillates with a periodicity of about 11 years, causing significant changes in climatic conditions on its surface. The region receiving the most light constantly shifts, leading to dramatic temperature variations and the potential generation of massive planetary-scale hurricanes. Moving 190 light-years away, the HD 10606 system, a yellow dwarf star is orbited by a gas giant with a highly variable climate known as HD 80606 bits. This planet rapidly approaches its parent star, experiencing extreme temperature changes within a short period before retreating to the system's periphery. The planet's atmosphere undergoes violent transformations, resulting in shock waves, hurricanes, and massive atmospheric emissions. HD 80606 bits' temperature roughly doubles within 6 hours during its closest approach to the star, leading to dynamic atmospheric phenomena. The planet's unique orbit and rapid climate changes make it a fascinating yet harsh celestial environment. Further exploration takes us 530 light-years away to the Kepler 36 system, where a yellow subgiant star is orbited by two planets, a rocky super-Earth and a hot mini-Neptune. These planets closely approach each other every 97 days, causing intense gravitational interactions and global cataclysms. The rocky planet's crust may crack and shift under the colossal forces, leading to earthquakes and eruptions of gigantic volcanoes. Kepler 36 bits, the super-Earth, has a mass 3.8 times that of Earth and a radius 1.5 times greater. The second planet, Kepler 36c, falls into the category of hot menace with a mass 7 times that of Earth and a radius 3.7 times greater. The unusual system's formation, characterized by the gravitational interaction between the planets, presents a fascinating celestial dynamic that challenges current scientific explanations. In conclusion, the exploration of these extraordinary celestial bodies, from potentially habitable planets to anomalous objects with unusual behavior, enriches our understanding of the complexity and diversity of the universe. Each discovery raises new questions and prompts continuous scientific inquiry, fostering a deeper appreciation for the wonders of the cosmos. In the vast expanse of space, asteroid streams and the mutual gravitational pull of two planets contribute to the distortion of their orbits, altering eccentricity and other parameters. As a result, the entire planetary system behaves chaotically and unpredictably, defying any accurate long-term predictions. Modeling reveals a 91% probability that the two planets will collide within the next 70 million years, generating numerous debris pieces that will disperse throughout the system, intensifying chaos. Such cataclysmic events may have occurred multiple times in a system located 434 light-years from Earth. In this distant system, a peculiar object referred to as Super Saturn orbits a young sun-like star from a distance of 4 astronomical units. This object, identified as a brown dwarf or a large gas giant, possesses a system of rings akin to Saturn's but significantly larger. Observations suggest the presence of at least 37 distinct rings, with the largest outer radius measuring about 6 astronomical units. The total mass of the circumplanetary disk surpasses that of Earth, and its behavior exhibits signs of randomness. Mathematical modeling indicates the instability of such structures, eventually leading to disintegration over several 100 million years. Within the ring system, a significant rupture of approximately 4 astronomical units hints at the presence of an exosatellite, a celestial body with a mass around 80% that of Earth. Observations also imply the existence of 2 more celestial bodies, each with a mass approximately 30% that of Earth, located about 0.25 astronomical units from the center of the brown dwarf. Simulations considering radiation from the parent star, heat flow from the gas giant, and tidal influences suggest that the celestial bodies making up the system could attain comfortable temperatures. The image viewed from an exosatellite's surface includes a vast sky dominated by the brown dwarf's glow, creating a unique climatic zone. The concept of rogue planets, celestial objects drifting freely in stellar space without orbiting a star, has intrigued scientists. Detecting such objects proves challenging due to their minimal thermal and light energy emissions. Recent advancements have identified 3 rogue planets with certainty and proposed over 24 candidates. The Milky Way could potentially host up to 100 billion rogue planets, marking the beginning of discoveries in this field. The closest confirmed rogue planet, known as I-855-714, lies 7.27 light-years away and was detected in 2014 with an orbital infrared telescope. With an extremely low temperature resembling a cool-off gas giant, this rogue planet emits little visible light. The presence of water in its atmosphere, discovered in 2016, suggests the existence of clouds made up of tiny ice particles. The origin of rogue planets remains uncertain, with 2 prevailing theories, one involving ejection from a regular planetary system and the other suggesting formation from compressed interstellar gas. While assumptions about rogue planets have long relied on hypotheses, technological advancements in observation equipment provide opportunities for practical testing. The evolving field promises further discoveries, challenging existing notions and expanding our understanding of these mysterious celestial wanderers. The likely surface temperature of the planet is approximately 250 K, equivalent to 23 degrees Celsius below zero. The celestial body's atmosphere encompasses a relatively warm layer about 100 kilometers thick, with a fluctuating density ranging from 4 to 1.2 milligrams per cubic km. This environment, comparable to Earth's conditions, is deemed potentially conducive to organic life. Interestingly, a planet need not be a massive gas giant to avoid freezing in the cosmos. In 2020, gravitational microlensing techniques detected a candidate for a rogue planet, yet its status awaits confirmation. Preliminary data suggests that this object, comparable in mass to Earth, is positioned anywhere from 30 to 180,000 light-years away. According to current scientific understanding, such a mass is more indicative of a rocky planet rather than a gas giant. This leads to the belief that the object may have originated in a protoplanetary disk of a planetary system, undergoing ejection due to cataclysmic events or the influence of a larger neighbor, eventually becoming a free-floating planet. The subsequent fate of the rogue planet is influenced by various factors. If its atmosphere is sufficiently dense, it could be thermally isolated, potentially maintaining a layer of ice on its surface. The interior, heated by radioactive decay, may keep most of its hypothetical ocean in a liquid state. Tidal forces, especially if it retained a moon upon ejection, could continue to deform and warm the lithosphere, offering a slim possibility for the existence of primitive anaerobic life forms. Current knowledge about rogue planets primarily stems from mathematical modeling and intricate calculations, relying on minute data gathered by orbital and Earth-based telescopes. The Cleopatra project, utilizing microlensing, aims to search for free-floating planets and objects in space, defining their parameters. Expected to launch in 2025, this interplanetary spacecraft will be equipped with an artificial intelligence component to process and analyze information, promising exciting discoveries. The potential destiny of rogue planets involves a minuscule chance of gravitational capture by a star, incorporating them into a planetary system. However, the majority are expected to wander for millions to billions of years, gradually cooling off and ultimately facing scenarios like being swallowed by black holes or succumbing to cataclysms in space. keeping their secrets hidden from mankind. In 2003, routine observations of the starry sky led to the discovery of a small yellow dwarf in the Phoenix constellation, later named WSP-96. In 2013, the Super WSP Orbital Telescope identified an exceptionally rarefied gas giant in close proximity to the star. Subsequent spectral analysis indicated a remarkably transparent atmosphere, practically devoid of water vapor. However, in 2022, the James Webb Space Telescope contradicted these findings, revealing thick cloud layers on the exoplanet. The James Webb Space Telescope, launched after 25 years of development, is positioned at the second Lagrange point, 1.5 million km from Earth, overcoming interference from Earth, the Moon, and the Sun. Its high-precision infrared sensors enable the observation of faint signals from distant space objects. Notable discoveries include the study of WSP-96 Bits, a hot Jupiter with unexpected atmospheric characteristics, challenging earlier interpretations. Beyond the unexpected findings, the telescope has made numerous exciting discoveries, such as an unusual system of 3 brown dwarfs located 69 light-years away. These cosmic bodies, larger than planets but not massive enough to be stars, contribute to the expanding knowledge of the universe. James Webb's unparalleled sensitivity has proven instrumental in shedding light on the mysteries of distant celestial bodies, promising further revelations as it continues its mission. Brown dwarfs are generally too small to sustain a stable thermonuclear reaction in their interiors, making them challenging to detect due to their low surface radiation. However, the James Webb Space Telescope's capability to primarily observe in infrared makes it adept at identifying objects that are nearly invisible in the optical range. In a particular system, the 2 primary components share similar characteristics. Located closely with a distance of approximately 2 astronomical units and a combined mass slightly exceeding 100 times that of Jupiter. Both objects exhibit relatively high temperatures, reaching 2,600 Kelvin. The third component in the system is situated at a much greater distance, around 100 astronomical units from the center, with a mass ranging from 14 to 23 Jupiter masses and a radius 20% larger than Jupiter. Despite being twice as cold as its more massive counterparts, this brown dwarf remains considerably warmer than gas giants in our solar system. Surprisingly, observations reveal that the outer layers of this brown dwarf contain not only typical components like water, methane, or carbon dioxide, but also minute particles of various silicon compounds, including quartz and more complex substances. The existence of these silicon clusters was theorized and predicted due to silicon's prevalence in the universe as a product of stellar thermonuclear reactions. The formation of the system likely involved a single gas dust cloud splitting into 3 clumps approximately 140 million years ago, possibly influenced by the gravitational pull of a massive celestial body. This separation prevented the formation of a self-sustaining thermonuclear reaction, resulting in 3 brown dwarfs rather than a single tiny star. James Webb's capabilities extend beyond observing individual objects to capturing vast space structures, such as the Kina Nebula, one of the largest stellar nurseries in our galaxy, located 8,500 light-years away. This nebula hosts giant clouds of interstellar gas and dust, along with thousands of stars, including unique objects like E8 Carini and WR25, each with luminosities several million times greater than the Sun. James Webb's infrared cameras have unveiled previously unknown stars within the dusty haze, contributing to our understanding of the continuous formation of young stars within the nebula. The telescope's reach extends to the very edge of the visible universe, capturing light from objects over 13 billion years old, providing a glimpse into the earliest times after the hypothetical Big Bang. Gravitational lensing, a rare phenomenon amplifying light from a source behind a massive body, played a crucial role in revealing a distant and ancient galaxy, estimated to be 13 billion years old, within the galaxy cluster SMX 723, located approximately 4 billion light-years away. James Webb's unique observations of objects at various distances and ages within the universe offer valuable insights into star formation processes, allowing astronomers to track the evolution of protostars and young stars in the Ina Nebula. The telescope's infrared senses enhance the chances of capturing shorter phases of this process that could last hours or days, providing a comprehensive understanding of star formation. The quest for exoplanets, which varies significantly in environment and size, has been advanced by various techniques. Kepler, launched in 2009, became the first space telescope designed specifically for exoplanet detection. Equipped with 42 charge-coupled devices (CCDs), with a total resolution of approximately 96 megapixels, Kepler's transit method proved instrumental in identifying over 3,500 exoplanet candidates within 3,000 light-years from Earth. This method relies on observing the decrease in a star's luminosity when a potential planet transits across it, with fluctuations indicating the object's dimensions and orbital period. Kepler's achievements include the detection of Kepler-37b, the smallest known exoplanet with a diameter just 35.7% that of Earth. The transit method, with its accuracy in measuring minimal changes in a star's spectrum, has also facilitated the identification of stars, brown dwarfs, and other celestial bodies. The ongoing advancements in observational technology, exemplified by James Webb, promise further exploration and understanding of the vast and diverse universe beyond our solar system. The presence of atmosphere dust and precipitation negatively impacts the effectiveness of Earth-based telescopes. This limitation has led to the utilization of automatic space stations for the exploration of objects beyond our solar system. Unfortunately, the Kepler Space Telescope, designed specifically for discovering exoplanets, encountered significant equipment failures in 2013, culminating in the termination of its science operations in 2018. Despite being the first of its kind, Kepler faced challenges in studying many of the identified remote and dim objects in satisfying detail. Address these limitations, the Transiting Exoplanet Survey Satellite, TSS, succeeded Kepler, launching on April 18, 2018. TESS aimed to locate rocky exoplanets orbiting the brightest stars within 200 light-years from the Sun. Utilizing the transit method, TESS is equipped with 4 refractors featuring a 24x24 deg field of view and a 10 cm aperture. Its unique orbit allows coverage of both the northern and southern parts of the sky, approximately 85% of the entire sky. TESS's cameras, with a resolution of 16.8 megapixels for each CCD, captured significant data during its mission. Among TSS's discoveries, TOI 700d stands out as an exoplanet comparable to Earth in size, residing in the habitable zone of its host star, TOI 700. The star is a red dwarf located just over 100 light-years away. Despite being tidally locked, with one side always facing the star, TOI 700 remains of scientific interest due to its potential rocky composition and an estimated surface temperature of 268.2 K TESS, having completed its main mission, continues operations and has discovered over 2,100 exoplanet candidates, contributing to our understanding of the cosmos. Beyond exoplanet exploration, NASA compiled a list of terrifying worlds in 2020, featuring 6 exoplanets with extreme conditions. One such example is TREES-2b, a black gas giant orbiting a yellow dwarf star 718 light-years away. TREES-2b absorbs over 99% of the light it receives, making it the darkest exoplanet known. Despite its eerie appearance, TREES-2b doesn't pose the most hazardous conditions in the universe. Another formidable exoplanet, 55 Cancri orbits a Sun-like star and was discovered in 2004. With a mass of approximately 8 Earth masses and tidally locked, 55 Cancri experiences scorching temperatures on its daytime side, reaching 2,400 degrees Celsius, while the nighttime side remains at 1,300 degrees Celsius. The planet's atmosphere contains helium, hydrogen, and significant amounts of carbon, potentially forming layers of graphite and diamonds in its interior. This inhospitable environment distinguishes 55 Cancri from other more habitable objects within its star system. In summary, advancements in space telescopes like TESS continue to deepen our understanding of distant celestial bodies, particularly exoplanets. The exploration of diverse and extreme environments contributes valuable data to the broader field of astrophysics, pushing the boundaries of our knowledge about the universe. The pulsar system hosts a celestial object positioned merely 0.36 astronomical units from the system center, indicating that the exoplanet known as PISP may have formed after a supernova event. Another hypothesis suggests the pulsar's formation resulted from the merging of two white dwarfs. Being the first of its kind, PISP's origin remains uncertain. The system is situated 2,300 light-years from Earth, with the exoplanet having approximately 4 times the mass of our planet and an orbital period of about 66 days. Despite the powerful radiation emitted by the pulsar, PISP, while destructive to approaching spacecraft, doesn't rank as the most dangerous exoplanet. Kepler-70b, the hottest known exoplanet, orbits the sub-dwarf star Kepler-70 with a surface temperature of 6,800 degrees Celsius. Despite its mass being 0.44 Earth masses and its radius 0.76 times that of Earth, its extreme temperatures make it a unique object. Kepler-70b's orbital period is just 345 minutes, resulting in a day lasting less than 6 hours. It frequently passes another object, Kepler-70c, at a distance of 240,000 kilometers, marking a remarkable proximity between planets in space. Similarly, WASP-12b, located 87 light-years away, exhibits extreme conditions due to its close proximity to its parent star, with a temperature reaching 2,200 degrees Celsius. Contrary to appearances, seemingly ordinary exoplanets like HD 189,733b can pose dangers. Despite its Earth-like appearance, this gas giant has winds reaching speeds of 8,700 km per hour, carrying silicate particles and glass precipitation. HD 189,733b, located 63 light-years away, has a diameter 1.1 times that of Jupiter and a constant surface temperature of approximately 930 degrees Celsius. The Hubble telescope revealed its foggy atmosphere with a reddish hue during transits, hinting at unique atmospheric conditions including water vapor, neutral oxygen, and unusual methane compounds. Exploration of ocean worlds. Planets covered entirely in water began with theoretical groundwork in the 1970s. The term denotes planets with surface oceans not concealed by ice, and calculations suggest they could form from a mass 8 times that of Earth. Depending on their distance from the host star, they may become ice giants or super, with radioactive decay causing melting and the formation of subsurface oceans. Such planets could have water layers over 100 kilometers thick and pressures reaching 20,000 atmospheres, leading to the formation of exotic ice varieties with densities higher than liquid water. In summary, the exploration of diverse exoplanets continues to unveil unique and sometimes hazardous characteristics, contributing to our understanding of the vast and varied cosmos. As technological capabilities improve, scientists remain vigilant, expecting more surprises and discoveries in the ongoing exploration of celestial bodies beyond our solar system. The ice, with a density of 1,650 kilos per cubic meter, settles at the bottom of the planet's ocean, forming a vast cryosphere that surrounds its more massive core. The opportunity to test these theoretical assumptions arose when scientists observed a small and dim star 42 light-years away, named GLA 1214. This red dwarf's diameter is 5 times smaller than the Sun, with a mass only 15.7% of the Sun's. GLA 124 is 300 times dimmer than our Sun, with a surface temperature of 3,000 K or 2,700 C. Despite its nondescript nature, a solitary planet, GLA 1214b, was discovered in its vicinity in 2009. With a diameter 2.5 times that of Earth, the exoplanet is 6.5 times heavier. Basic calculations show that the freefall acceleration on GLA 1214b's surface is 91% of Earth's. Judging by its average density of approximately 1,870 kilos per cubic meter, the assumption that the astronomical body is 75% water or water ice and 25% other substances seems reasonable. The exoplanet is classified as an ocean planet due to its proximity to its host star, with an average distance of 2 million km, 75 times smaller than Earth's distance from the Sun. The orbit eccentricity is high at 27, slightly more than Pluto's, resulting in scorching surface temperatures on Glia 1214 bits. Spectroscopic investigations of its atmosphere are challenging, with ambiguous results. If it is indeed an ocean planet, the atmosphere should predominantly consist of water vapor with accompanying gases. Interestingly, no lines of hydrogen, helium, or complex substances have been detected in the planet's spectrum. The atmospheric conditions on Glia 1214 bits resemble those inside a giant steam boiler. The atmospheric pressure in its lowest strata should be at least 15 tons, equivalent to Earth's, blurring the border between the ocean and atmosphere due to thermodynamic equilibrium. We look deeper into the ocean's lowest strata. The pressure increases until reaching a depth of 100 kilometers, enabling water to remain in a liquid state, even at high temperatures. The bottom is estimated to be dense and heavy ice, with a thickness exceeding 5,000 kilometers. Unfortunately, the chances of life evolving on an ocean planet are slim due to the lack of vital microelements. Despite these challenges, studying ocean planets remains scientifically intriguing, with NASA's mathematical modeling estimating billions of such planets in the galaxy, featuring diverse conditions. A giant cloud, hundreds of light years away, conceals unborn and exploding stars, permeated by lethal ionizing radiation and fiery vortices, the birthplace of stars known as stellar nurseries. Scattered across the galaxy, these nebulae, made of interstellar gas and dust, are compressed by gravity forces. The Orion Nebula, located 1,344 light-years from Earth, is one such structure extensively studied since the early days of astronomy. The Hubble Space Telescope provided the first images of the Orion Nebula in 1993, revealing a rich diversity of colors. Spectral analysis uncovered unusual bright green lines, initially perplexing scientists. However, further research clarified that the light emanated from extremely rarefied and ionized oxygen, not a hypothetical element nebulum. The Orion Nebula houses over 3,000 discovered stars, giant interstellar gas clouds, and numerous protostars. The vastness of the nebula, approximately 23 light-years in diameter, showcases various areas, including the trapezium, an open star cluster with 8 main components. Theta 1 Orionis C, the most massive and brightest star in the cluster, illuminates the surrounding nebula. The interaction of stars, gas, and protostars within the nebula adds to its complexity. The overall mass concentrated in the Orion Nebula is around 10,000 solar masses. This detailed exploration of GJ 1214 bits and the Orion Nebula underscores the intricate nature of celestial bodies and the ongoing fascination with unraveling the mysteries of the universe. Journeying a few light-years away from the trapezium, we encounter another intriguing system, Theta 2 Orionis. Comprising 3 gravitationally bound stars situated near the Orion Bar, an extensive feature of hot gas emitting bright light. This area was initially challenging to study due to dense dust clouds. Thanks to the James Webb Telescope, more detailed images have revealed the system's components. The first star in Theta 2 Orionis is slightly less massive and luminous than the trapezium's largest star, with a surface temperature of about 35,000 K. The second star is 15 times more massive than the Sun and 12,000 times brighter, while the third star, weighing 5 solar masses, has a temperature approaching 14,000 K. Beyond just bright stars, James Webb's infrared cameras detected previously unseen objects hidden within the gas and dust clouds. Approximately 180 dense dark protoplanetary disks, known as props, were discovered at the heart of the Orion Nebula. One notable example is Orion 29468-6, a young protostar about 1 million years old, surrounded by a gas and dust disk measuring about 300 astronomical units in diameter. Observing its structure and size due to its alignment with Earth, scientists anticipate it will enter the main sequence phase in a few million years, possibly accompanied by a system of exoplanets and satellites. Envisioning the night sky of these celestial bodies reveals a spectacular sight, featuring a multicolored luminous veil illuminated by numerous close and bright stars. The occasional presence of tremendous swirls of glowing gas covers half the sky, transforming the night into a translucent twilight. Venturing further, a broader view of the region shows the nebula filled with scattered gas. The central part contains highly ionized hydrogen actively absorbing high-energy stellar radiation, with temperatures reaching 10,000 Kelvin. However, temperatures sharply decline towards the region's edge, creating temperature and pressure contrasts that, along with collisional forces, induce material movement, generating tremendous currents and vortices. Calculations suggest that some of these currents can attain speeds of up to 50 km/s, with sizes surpassing the solar system. Additionally, strands of cool molecular hydrogen, mixed with methane, ethane, and water, extend for several light years. Delving deeper into the nebula, a vast cloud of cooler, denser gas envelops the central region, creating a mesmerizing multicolored curtain of light. Behind this curtain lie hundreds of space objects, invisible in the optical range but revealed by infrared cameras. Combining data from various sources, astronomers have identified around 700 protostars at different evolutionary stages within this region. These protostars, forming within regions of gravitational compression of large interstellar gas clouds, give rise to giant vortex disks. These disks, influenced by the growing magnetic field of the young star, exhibit ultra-fast motion and create large-scale vortices in hemispheres known as Herbig-Haro objects. These objects, resulting from major cosmic collisions, are highly unstable, changing color and shape rapidly, and typically disperse over tens of thousands of years. In the midst of stellar nurseries, Herbig-Haro objects, and protostars, the Orion Nebula is part of a larger cosmic structure known as the Orion Cloud, stretching for hundreds of light years. This region includes the well-known Horsehead Nebula, characterized by its distinctive shape, and the impressive B-Loop, a 300 light-year-sized emission nebula formed 3 million years ago by consecutive supernova explosions. Despite its beauty, the Orion Nebula is fragile by cosmic standards, losing approximately 60% of its original material. In around 100,000 years, it is predicted to be stripped of its remnants, leaving behind an open star cluster. Continuing our celestial journey, our next destination is 202 light-years from Earth, where we encounter K2D-141, an orange dwarf star with a mass about 7 times that of the Sun and a radius 68% of the Sun's. The star's temperature, at 4,600 Kelvin, is approximately 20% lower than that of the Sun. Orbiting this star at just 0.007 astronomical units is the intriguing exoplanet K2D-141b. This rocky world is 5 times the mass of Earth, with a radius 1.5 times that of our home planet. The heavy metallic core accounts for 20 to 50% of the planet's overall mass, and its surface gravity is estimated to be at least twice as strong as Earth's. Tidally locked to its parent star, it completes a full orbit in about 6.5 hours. As we explore this diverse cosmic landscape, from the Orion Nebula to distant exoplanets, the intricacies of celestial formations, stellar evolution, and the dynamic interplay of forces across vast cosmic distances continue to captivate our understanding of the universe. Observations indicate that the temperature on the day side of the planet reaches 3,270 K or 3,000 degrees Celsius. This is sufficient not only to melt most metals but also to effectively evaporate them. The day side is believed to be covered with a perpetual lava ocean, with an exotic atmosphere composed of heavy metal and silicate steams. In contrast, the night side is extremely cold, with temperatures tens of times lower than the day side, creating a sub-zero environment. Mathematical modeling suggests that this temperature difference results in powerful winds with speeds reaching 1.75 km/s, causing continuous and intense rumbling on the planet's surface. It is theorized that on the night side, atmospheric streams condense and precipitate as fiery rain, forming lava rivers. This molten material eventually makes its way back into a magma ocean to evaporate once again, creating a fiery circulation. However, this cycle only affects a limited part of the night side, as evaporated elements from the day side do not reach the central region, resulting in a freezing desert with layers of solid rocks. Remarkably, K21141 bits is not the hottest planet known. For instance, KELT 9 bits, located 670 light-years away, has a surface temperature of 4,600 Kelvin, equivalent to 4,330 degrees Celsius. This exoplanet's parent star, KELT9, is a whitish blue star with a mass 2.6 times that of the Sun and a diameter 2.3 times larger. KELT9 bits, a hot gas giant, experiences extreme conditions due to its proximity to the star, gradually losing its atmosphere to powerful stellar winds. Estimates suggest that the exoplanet loses up to 68 Earth masses every billion years, potentially leading to the complete loss of its atmosphere over time. Moving on to V391 Pegasi, a white dwarf located 4,570 light-years away. It has a temperature of nearly 30,000 Kelvin. V391 Pegasi b, a gas giant 3 times the mass of Jupiter, survived its progenitor star shedding its outer layers. Mathematical modeling indicates that the planet found itself within the star for a period before ultimately melting. Despite the dramatic changes in its orbit and parameters caused by the star's collapse, the exact nature of V391 Pegasi b before its immersion into the star remains unknown. Exploring further into space, we encounter unique celestial objects such as pulsars, neutron stars spinning at incredible speeds. One such pulsar, located around 4,000 light-years away, emits powerful electromagnetic radiation pulses. The exoplanet orbiting this pulsar faces continuous exposure to lethal radiation, completing a full orbit in just 2 hours. Its surface experiences extreme conditions due to the relentless radiation. Concluding our journey, we come across a celestial body situated close to a pulsar, with a diameter of 20 kilometers and a mass approximately 1.4 times that of the Sun. The exoplanet's surface is constantly exposed to lethal radiation, making it a hostile environment. Despite its proximity to the pulsar, the planet's mass is around 330 times that of the Earth, with gravity on its surface 20 times stronger than on Earth. The planet is believed to be composed mainly of crystallized carbon under high pressure, possibly originating from a debris field left by a white dwarf after the end of its life cycle. In summary, these diverse celestial objects showcase the extreme conditions and fascinating phenomena that exist in our vast universe, emphasizing the intricate interactions between stars and their orbiting planets. Classifying the exoplanet remains a challenging task due to its unique characteristics, making it one of the most dangerous and hostile worlds in the cosmos. Located 650 light-years away, IRC plus 10,216, also known as CWNS, is a majestic star with a radius that may reach 560 times that of the Sun at its pulsation peak. Placing CWNS hypothetically in our solar system would position all planets up to Mars beneath its surface, even brushing the inner boundary of the asteroid belt. Despite its surface temperature of 2,300 K, the star emits 8.5 thousand times more energy than our Sun, typical of a red giant in its final life stage. Leonis, estimated to be several billion years old, evolved from a white-blue star into a red giant. The star's outer layers became more rarefied and unstable as it expanded, leading to a blood-red hue. The helium flash, a complex process, transformed helium nuclei into carbon, heating the star's outer layers. This cyclical process results in occasional changes in the star's luminosity. CWNS has a 649-day pulsation cycle, with a luminosity at its peak 11,300 times brighter than the Sun and 6,250 times brighter at its lowest. The star loses significant mass, about 4*10^22 tons, annually, forming a complex circumstellar nebula with an elaborate structure including bulges, pockets of gas, arcs, and irregular rings. Magnetic activity and stellar wind, generated by the unstable star, contribute to these formations. The nebula surrounding CWNS, over 69,000 years old and 1.5 times the mass of the Sun, exhibits an intricate chemical composition. Spectral analysis reveals around 70 different chemical compounds, including carbon dioxide, water, and ammonia. Despite the possibility of past planets, none have been detected, though mysterious shifts in the gas and dust cloud around the star were observed in 1994 and 2017. A hypothetical stellar companion may explain these phenomena, but attempts to detect it have been unsuccessful, possibly due to the nearby nebula. Leonis has a comparatively high water content in its environs, challenging the accepted model of red giants. Observations in 2009 showed water vapor forming in the upper layers of the giant, deviating from traditional models of oxygen depletion. A new hypothesis suggests the destruction of silicon oxides and carbon by powerful ultraviolet radiation, releasing oxygen that reacts with hydrogen to form hot water vapor. Despite its paradoxes, water vapor makes up only a small fraction of Leonis's overall mass. As a red giant in its autumn years, Leonis is expected to deplete its stellar fuel in the next 10 to 30,000 years. Following a powerful explosion, it will transform into a white dwarf, eventually fading over billions of years to become a mysterious black dwarf. The shockwave and extreme temperatures generated during this transformation will create new elements not present in a star's interior, contributing to the formation of new celestial objects. The universe's constant evolution involves global cataclysms and destruction, but within every storm, there are fresh rays of light. The interiors of stars have incredibly high temperatures, essential for thermonuclear synthesis, the main energy source for all stars. This process involves the fusion of hydrogen atoms to produce helium, releasing vast amounts of energy. However, hydrogen-helium synthesis is not the only process that heats up stars. Chemical reactions involving other elements, such as lithium, carbon, or oxygen, also contribute to the extreme conditions within stars. Elements such as sulfur, magnesium, or phosphorus, with higher charges, repel each other more robustly, requiring more energy to overcome this resistance. When a main sequence star depletes its hydrogen supply, it expands and cools, eventually becoming a red giant. The red giant continues to burn through thermonuclear reactions of helium transforming into carbon and oxygen. As the star becomes unstable, it sheds its outer layers and goes supernova, leaving behind a white dwarf with no resources for further thermonuclear reactions. When the mass of a star is higher than a certain value, heavy thermonuclear synthesis may become the star's main energy source, leading to the classification of Wolf-Rayet stars, discovered in 1867 by French astronomers Charles Wolf and Georges Rayet. These stars are rare, with only a few hundred identified in our galaxy. Wolf-Rayet stars are subdivided into three main sequences based on the prevalent element in their spectra: nitrogen, carbon, and oxygen sequences. The hottest star in the known universe falls into the oxygen spectral sequence category. Discovered in 1971 and now known as WR102, this star has a surface temperature over 210,000 Kelvin, making it approximately 36 times hotter than our Sun. With an estimated luminosity over 380,000 times that of the Sun, WR102 is located about 10,000 light-years away in the constellation Sagittarius. Despite its high luminosity, it is not visible to the naked eye due to its distance. WR102 belongs to the rare Wolf-Rayet star class W2, characterized by a high oxygen content and minimal hydrogen. Only 9 such stars have been discovered to date, with 4 in the Milky Way and 5 in other galaxies. Oxygen spectral sequence stars are rare due to the limited number of potential Wolf-Rayet stars with a mass of at least 40 solar masses, and their representation as the final stage of evolution for such stars. This stage lasts from a few thousand to 10,000 years, a relatively short duration in astronomical terms. WR102, while comparatively modest in dimensions, has a dense structure with a radius measuring 58% that of the Sun and an estimated mass of 15 to 18 solar masses. Despite its dense structure, the star exhibits an exceptionally powerful stellar wind with particles reaching speeds over 5,000 km/s, causing it to lose substantial mass over time. WR102 is surrounded by a gas envelope exposed to ultraviolet radiation and a strong stellar wind, leading to the contraction and ionization of the envelope, creating an intricate structure of protuberances and arches. The gas cloud around WR102 may be remnants of its former hydrogen outer layer or formed by the particle flow emitted by the star. WR102 is not the only intensely hot object in the universe. Other stars like W142, W30A, W93b, and the Bug Nebula NGC 6302 have surface temperatures around 200,000 Kelvin. Neutron stars, born with temperatures reaching 100 billion Kelvin, cool off rapidly due to active neutrino emissions. Returning to WR 102, it is currently in its autumn years. Unlike main sequence stars, Wolf-Rayet stars do not expand in their final life stages due to their substantial mass holding their material together in a dense and hot ball. However, after losing mass through stellar wind, WR 102 appears ready to go supernova in the next 1,500 years, according to current estimates. Given its distance of 10,000 light-years from Earth, the supernova event may have already occurred, potentially accompanied by an extra-powerful gamma-ray flare. Fortunately, Earth is far enough to avoid any perilous effects of such emissions. WR 102, composed of heavy chemical elements, will eventually contract to a critical point after the supernova explosion, leading to robust proton and neutron capture processes. These processes will form heavier elements, including transuranian ones, and the remnants of WR 102 will transform into a neutron star, releasing heat into space. This material may later contribute to the formation of a new planetary system over billions of years. Previously considered the largest star known, Uyscuti, located 9,500 light-years away, was surpassed by Stephenson 2-18 or RSGC 2-18, situated approximately 20,000 light-years away in the Scutum constellation. Part of the open cluster Stephenson 2-18 was cataloged in the 1990s but remained obscured by giant cosmic dust clouds until 2020. This giant star retains its original name despite potential discrepancies in its association with the Stephenson cluster. Stephenson 2-18 is characterized by its enormous size, with a radius potentially exceeding 1,900 times that of the Sun and a volume over 5 billion times that of the Sun. In summary, the universe is home to a variety of intriguing celestial objects, from Wolf-Rayet stars to giant stars like WR 102 and Stephenson 2-18. Each of these objects offers unique insights into the life cycles and extreme conditions present in the vast cosmos. Scientists have gathered astonishing data about the size of Stephenson 2-18, revealing that its estimated radius could reach up to 1.2 billion kilometers, which is 10 times the distance from Earth to the Sun or 2,150 times the radius of the Sun. This implies that the supergiant's volume is about 10 billion times that of the Sun. If placed at the center of the solar system, Stephenson 2-18 would easily engulf Saturn along with its rings and moons, not to mention the terrestrial planets. Interestingly, it would take light approximately 8.5 hours to traverse the length of this gigantic star's equator, equivalent to the time sunlight takes to reach Pluto at its farthest orbit point. Despite its impressive dimensions, Stephenson 2-18's luminosity is estimated to be 440,000 times that of the Sun, and its surface temperature is relatively low at about 3,200 Kelvin. This places it in the red band of the light spectrum, earning it the classification of a red supergiant. This lower temperature means that most of the star's radiation is in the visible and thermal spectra, with negligible amounts of ultraviolet and X-ray radiation. Despite its significant size and luminosity, Stephenson 2-18 remains invisible to the naked eye from Earth due to its low surface temperature and the presence of stardust and gas clouds that obscure the star. The mass of Stephenson 2-18 is yet to be determined, but if it shares similar internal composition with Uyscuti and other supergiants, it should fall within the range of 20 solar masses. This would result in an extremely low average density for supergiants, almost equivalent to the density of Earth's atmosphere at an altitude of about 90 kilometers above sea level, near the border with space. It's remarkable that thermonuclear energy, the source of a star's glow, is sustained in such conditions. Supergiants are often variable in terms of their luminosity, and this unpredictability is attributed to their status in the final stages of their life cycles. Stars with original masses ranging from 10 to 40 times that of the Sun are deemed eligible to become red supergiants. As they evolve, these stars rapidly burn out hydrogen, turning it into helium, and subsequently rely on fusion reactions of helium, carbon, oxygen, and lithium as their chief energy source. The life expectancy of supergiants is relatively short, just a few million years. As they evolve, they expand rapidly, losing mass due to strong solar wind, stardust clouds, and surrounding gas. The prospect of habitable zones around supergiants like Stephenson 2-18 is intriguing, given their enormous dimensions. The habitable zone of Stephenson 2-18 is expected to be vast, with its middle located approximately 663 astronomical units from the star's center. This corresponds to 20 times the distance from the center of the Sun to Pluto's orbit, and the area of the habitable zone is anticipated to be 1 billion times that of the Sun. While scientists acknowledge the possibility of planetary systems around supergiants, the unstable conditions and short lifespan of the stars make the chances relatively slim. As of now, no confirmed exoplanets have been discovered around Stephenson 2-18, given its considerable distance from Earth, with its light taking 20,000 years to reach us. In the distant future, Stephenson 2-18 might undergo a supernova or hypernova event, hurling its outer layers away and gradually cooling off to form a nebula. The former core may transform into a neutron star or a black hole based on its mass. This material could contribute to the formation of a new planetary system over billions of years. Before telescopes were invented, the Milky Way appeared as a luminous strip across the heavens, giving rise to numerous legends. However, it took thousands of years of scientific progress to understand that the Milky Way consists of the dispersed light of billions of stars too remote to be individually distinguished. Emmanuel C. suggested the idea of stars forming part of a single structure with enormous dimensions in 1755, and he also proposed that some nebulae could be remote star clusters or other galaxies. This insightful guess was ahead of its time, with contemporaries initially dismissing it. It wasn't until the early 20th century that advancements in observation equipment confirmed the existence of other galaxies. Edwin Hubble's classification system in 1936 laid the groundwork for understanding galaxies, placing the Milky Way in the category of barred spiral galaxies. The Milky Way, our galaxy, is ancient, with stars in its central globular clusters dating back around 13 billion years. Simultaneously, active star formation regions indicate that the Milky Way continues to give birth to new stars. With a diameter of 200,000 light-years and at least 200 billion stars, along with brown dwarfs, planets, and cosmic dust, the Milky Way is a vast and complex structure. Dark matter constitutes around 90% of its overall mass, contributing actively to gravitational interactions. Despite being mostly invisible, dark matter's presence is deduced through calculations based on star trajectories. The center of the Milky Way is observed through the so-called Bis window, an area with lower amounts of dust. Like many spiral galaxies, the Milky Way contains a supermassive black hole, known as Sagittarius A*, surrounded by an accretion disk with a radius of approximately 3 light-years. With a mass of 4.3 million solar masses and a radius smaller than 16 million km, Sagittarius A* is the closest supermassive black hole to us. In conclusion, the universe is teeming with fascinating celestial objects, from supergiants like Stephenson 2-18 to the intricate structure of galaxies like the Milky Way. Each of these entities contributes to our understanding of the vast cosmos and the processes that shape it. The first data about the nature of the object at the center of our galaxy, acquired through long observations and calculations, culminated in obtaining the first image on May 12, 2022, using the EHD network of radio telescopes. This confirmed earlier hypotheses, revealing a highly populated area in the center of our galaxy with more than 6,000 stars detected within 3 light-years from the black hole. Some of these stars have well-defined orbits, such as the white-blue star designated S62, situated 17.8 astronomical units away from the black hole at its closest approach, moving at 6.7% of the speed of light. The application of classical mechanics laws becomes inadequate due to relativistic effects, as illustrated by the shift in the axis of its orbit by 75 angular minutes with each completed orbit. Traversing this region in space unveils large star clusters with a total mass of around 1 million solar masses, and further away, approximately 200 light-years distant, another massive black hole is likely to be present with a mass around 100,000 times that of the Sun. Moving beyond, we encounter the central molecular cloud, a regularly shaped area spanning 1600 to 19,000, 900 light-years with a mass exceeding 60 million solar masses. Abundant stellar nurseries, gas nebulae, protostars, and remnants of supernovae exist within this gigantic cloud, primarily composed of dense hydrogen with temperatures ranging from 50 to 600 Kelvin. Spectral analysis reveals the presence of carbon monoxide, methyl alcohol, and hydrocyanic acid, in addition to hydrogen. Retreating from the Milky Way center, we find it surrounded by a bulge, a bright elliptical formation with a length of 10,000 light-years and a transverse diameter of approximately 7 light-years. The bulge's total mass is estimated to be 10 billion times that of the Sun. Due to the elongated shape of the bulge, it forms the so-called bar, extending for about 13,000 light-years and serving as the base for the spiral galactic arms. It is in this region that we find the star cluster Stephenson 2, housing the largest known star, Stephenson 2 at 18, with a radius 2,150 times that of the Sun. While chances of finding exoplanets orbiting Stephenson 2 at 18 are minimal, the galaxy's center is home to billions of stars and potentially numerous exoplanets. However, the likelihood of encountering a habitable world among this multitude is lower than in less densely populated areas due to the destabilizing effects of closely positioned stars on exoplanet orbits and their lethal radiation. The habitable zone, resembling a ring with a radius of 29,000 light-years, contains star systems with favorable conditions for biological life genesis. Moving away from the center, the journey takes us to the most impressive part of the Milky Way, the galactic disk, comprising the thin and thick disks with different properties. The thin disk, spanning 1,000 to 1,300 light-years in thickness and a visible radius of 50,000 light-years, contains around 80% of the galaxy's visible mass. The thick disk, 4 times as thick, is composed of old stars and lacks interstellar gas. Observations and modeling indicate the Milky Way may have swallowed another galaxy, Ga Enceladus, contributing several billion stars and significant amounts of interstellar gas and dark matter. The galactic arms, such as the Scutum Centaurus arm and the Paris arm, are areas of high star count and concentrated interstellar gas, promoting star formation rates 3 to 5 times higher than the galaxy's average. As stars drift away from open clusters, they populate the arms. The Orion arm, linked to the Canis Sagittarius arm, houses the solar system, located 27,000 light-years away from the galaxy's center. The Great Rift, a dark abyss seen from Earth's perspective, is filled with massive clouds of interstellar gas and dust-emitting radio waves and thermal energy. Its potential as a stellar nursery is yet to be realized. Continuing beyond the disk, we explore the halo, stretching up to 260,000 light-years from the galaxy's center. This spherical component contains globular clusters with remarkably old stars over 12 billion years old and stellar streams like the Sagittarius stream, composed of several thousand stars. The halo also contains large amounts of gas with temperatures reaching millions of Kelvin and scattered dark matter forming the dark halo, stretching up to 2 million light-years. The halo encompasses a wide array of celestial features, including bright stars, clusters, and vast amounts of gas and dark matter, contributing to the overall understanding of the Milky Way's structure and evolution. The dark halo, which emits no electromagnetic radiation and is only detectable through gravitational interaction, remains a perplexing mystery. Despite this, it significantly contributes to the overall stability of our galaxy. Distances from the Milky Way and other galaxies are staggering, ranging from millions to billions of light-years due to the cosmological expansion of the universe. The constant growth in the distance between Earth and remote objects results in a phenomenon known as redshift, making the light from these objects appear older than it actually is. Some galaxies exhibit blue shift in their spectra, indicating motion towards us. An example is the galaxy M86 in the Virgo cluster, approximately 52 million light-years away, moving towards the Milky Way at a speed of about 244 km/s. M86 sheds interstellar matter as it moves through the Virgo cluster, leaving long trails of warm ionized hydrogen behind. M86 is associated with the almost destroyed spiral galaxy NGC 4438, with several filaments suggesting a past collision. Another noteworthy galaxy, ESO 137-001, part of the Able 3627 galaxy cluster, is located 227 million light-years away, weighing 5 to 14 billion solar masses. It exhibits a collision with interstellar gas pressure inside the cluster, resulting in gas being blown out and forming tails that extend up to 260,000 light-years. The galaxy's life expectancy diminishes as it loses interstellar gas, impacting the structure of its spiral arms and central bulge. The Baby Boom galaxy, located around 12.2 billion light-years away, sees the birth of approximately 4,000 stars annually, providing valuable insights into the early stages of the universe's evolution. The Sombrero galaxy, or M104, situated 30 million light-years away, features a massive ring of dust and cold hydrogen, serving as a stellar nursery. The peculiar inner structure reveals a collision of two galaxies, with surviving structures observable. Concluding the galactic parade, the Black Eye Galaxy M64 showcases an intricate inner structure with an inner disk and bulge rotating opposite to the outer ring. Its unique makeup likely resulted from the collision and merger of two smaller galaxies in the distant past. Expanding beyond our galaxy, the solar system consists of a single star in its main sequence stage, known as the Sun, and 8 planets with their satellites. The remotest known planet is Neptune, with an orbit radius of about 30 astronomical units. However, the farthest object discovered, far out, lies 132 astronomical units away. The solar system extends beyond, with the hypothetical Oort cloud starting around 2,000 astronomical units from the Sun. Moving further, there are over 50 billion stars in our galaxy, each potentially hosting its own planetary systems. The diversity and vastness of these celestial objects contribute to the richness and complexity of the universe, offering a wide range of phenomena for scientific exploration and understanding. Within a radius of 20 light-years from the Sun, the stars exhibit remarkable diversity, ranging from dim and cold brown dwarfs to bright and well-known objects like Sirius and Proxima Centauri. Some of these stars host their own planetary systems, with the potential to nurture and sustain life. An example is GJ832c, located 16.1 light-years away, sharing similarities with Earth in terms of temperature and orbit. However, given our current technological limitations, an interstellar spaceship traveling at 17 km/s would take an impractical 300,000 years to reach this exoplanet. The solar system, along with its neighboring stars, is situated within the Orion Arm, a segment of the Milky Way containing approximately 400 billion stars and potentially over 1 trillion exoplanets. The Milky Way itself boasts a main diameter of about 100,000 light-years, with a stellar halo that may be twice as extensive. A well-defined bulge exists at the galaxy's center, approximately 3,000 light-years thick. The Milky Way is part of the Local Group, a structure encompassing over 50 galaxies within a diameter of around 10 million light-years. Moving up the cosmic hierarchy, the Local Group is a component of the Virgo supercluster, a colossal structure comprising over 30,000 galaxies within a space of about 150 million light-years. This supercluster exhibits a flattened shape, with approximately 60% of its objects forming a flat sheet around 10 million light-years thick. Beyond the Virgo supercluster lies the Laniakea supercluster, encompassing several galaxy superclusters, including the Virgo supercluster and the Great Attractor. With a mass of around 100 quadrillion solar masses, the Great Attractor's gravitational influence extends approximately 250 million light-years from Earth, remaining an unsolved mystery due to the Milky Way obstructing direct observations. Expanding further, the large-scale structure of the universe reveals intricate patterns of galactic filaments, walls, and voids. The Hercules Corona Borealis Great Wall, spanning a colossal 10 billion light-years, stands as a testament to the vastness of cosmic structures. Despite the mystery surrounding such colossal clusters, they challenge the prevailing theories of universal evolution, suggesting unexpected formations. As the cosmic perspective broadens, the observable universe is perceived as a sphere with a diameter of approximately 93 billion light-years. According to the theory of relativity, interactions are confined within this sphere, termed the meta-galaxy. Hypothetically, extragalactic objects lie beyond this visible boundary, eluding current scientific study. Anomalies in the movements of celestial bodies at the edge of the visible universe hint at the gravitational influence of massive structures beyond the meta-galaxy, fueling a plethora of hypotheses. Some hypotheses delve into the metaphysical, proposing that beyond the meta-galaxy, concepts of time, space, and physical laws as we understand them may cease to exist. Others explore the possibility of a multiverse where each universe operates under distinct physical laws. The most radical hypotheses entertain the notion of our universe as a simulated reality, controlled by beings or civilizations beyond our comprehension. While these theories remain speculative, the sheer vastness of space and the limitations of our current understanding inspire contemplation. The expanding universe, should it persist, foretells a future where objects gradually vanish beyond the event horizon, leaving the cosmos immersed in eternal darkness. Ursula K. Le Guin's poetic sentiment echoes the idea that silence and darkness are essential to perceive the brilliance of stars, symbolizing the profound mysteries awaiting discovery beyond our cosmic horizon. The concept under discussion revolves around the birth and eventual demise of everything in existence. In the vastness of the universe, every object from subatomic particles lasting mere tenths of a second to microorganisms with lifespans of hours to days has its unique beginning and end. Even human life with an expectancy spanning several decades is not exempt. Stars, after existing for millions or billions of years, ultimately burn out. The profound question emerges: what about the universe itself? Will it too meet its end, and what will transpire post its hypothetical demise? Initially, proponents of the theory of the stationary universe or steady-state universe argued that the cosmos is eternal, with no beginning or end, existing in a perpetual state of equilibrium. However, scientific observations in the 1910s and 1920s contradicted this theory. The emergence of the Big Bang theory, rooted in Albert Einstein's general theory of relativity, gained prominence in the scientific community, offering a comprehensive explanation for the universe's genesis and evolution. According to the Big Bang theory, the destiny of the universe hinges on dark energy, a theoretical force propelling space expansion. While details about dark energy remain elusive, the age of the universe, calculated from the moment of the Big Bang, is estimated at slightly under 14 billion years. The universe's expansion, influenced by dark energy density, could result in perpetual expansion or a reversal leading to a compression into a singularity. The scientific community contemplates two plausible scenarios: the Big Rip and the Big Crunch. The Big Rip postulates an ever-accelerating expansion, causing galaxies, star clusters, and ultimately matter itself to disintegrate. This progression culminates in a state where physical laws cease to exist. On the contrary, the Big Crunch envisions a contraction of the universe due to gravitational forces exceeding expansion forces. In this scenario, galaxies merge into superclusters, leading to a compressed universe with rising temperatures, culminating in a singularity. The critical concept involves the expansion of space, analogous to a balloon being inflated. As space expands, objects placed further apart experience accelerated separation. The event horizon marks the point where this expansion exceeds the speed of light, rendering distant objects beyond observational reach. The consequences are depicted as a gradual disappearance of galaxies, star clusters, and, eventually, our Sun. The Big Rip scenario envisages an unbridled expansion, causing the breakup of galaxy clusters, stars, and even atoms into subatomic particles. Matter would cease to exist, and physical laws, as we know them, would unravel. In contrast, the Big Crunch entails a reversal of expansion, leading to a contraction of the universe. Galaxies merge into superclusters until the entire universe shrinks into a singularity. With successive contractions, temperatures rise, resulting in the annihilation of celestial bodies and the collapse of matter into an enormous cloud of plasma. A variation of the Big Crunch is the Big Bounce theory, proposing a cyclic pattern where a singularity following the Big Crunch triggers another Big Bang, perpetuating the cycle indefinitely. The uncertainty lies in our limited understanding of dark energy, preventing a definitive prediction of which scenario will prevail. Despite the ambiguity surrounding the universe's ultimate fate, the laws of physics delineate four distinct cosmological epochs. We currently reside in the Stelliferous era, characterized by the formation of stars from interstellar gas. The subsequent degenerate era will witness the cooling and transformation of celestial objects into white dwarfs, neutron stars, or black holes over trillions of years. In the black hole era, clusters of black holes may form, either merging or evaporating over time. The final epoch, the dark era, envisions a universe dominated by dark matter annihilation and proton disintegration, leading to a vast ocean of elementary particles. In conclusion, the evolution and destiny of the universe encompass intricate theories, each proposing a unique narrative of cosmic existence. The limitations in our understanding, particularly regarding dark energy, contribute to the uncertainty surrounding the duration and nature of these scenarios. The laws of physics, while providing a framework for these cosmic epochs, also imply that the universe, as we comprehend it, cannot endure indefinitely. The unfolding epochs paint a vivid picture of the eons to come, offering both scientific curiosity and existential contemplation. Hawking radiation dictates that smaller black holes undergo more intensive evaporation, depleting them of matter and energy over a staggering period of 10-100 years, often referred to as a googol. Eventually, the universe will be left with lifeless expanses of space containing remnants from previous epochs, such as photons, electrons, positrons, neutrinos, and quarks. Electrons and positrons may collide, resulting in annihilation. The universe in this state could endure practically forever until the occurrence of the next big crunch or big rip. Regardless, humanity's existence would likely be long gone by then. Our current stelliferous era, in which Earth remains habitable, is expected to last for another billion years before succumbing to the intensifying glow of the Sun. Approximately 5 to 6 billion years later, the Sun, having transformed into a red giant, will shed its outer layers to become a white dwarf. However, contemplating what happens after the death of the universe is an exercise in futility. The absence of time and space as we know them, even in scenarios like the Big Bounce theory or the Big Crunch theory, makes it impossible to predict or fathom. Whether a new Big Bang occurs, giving rise to a fresh universe with new galaxies and stars, remains beyond our grasp, much like the mysteries of the universe before ours. The profound silence and darkness enveloping these unknowns persist, leaving humanity to remain oblivious to the cosmic cycles. As we conclude this journey through the universe, there is an acknowledgement of the countless celestial wonders yet to be discovered. Billions of stars and trillions of planets harbor secrets awaiting unraveling, promising more educational episodes on the mysteries of the universe in the future. The exploration of outer space unveils a plethora of unusual celestial bodies, each a unique anomaly by space standards. These objects range from exoplanets strikingly similar to Earth to those shrouded in perpetual darkness or engulfed in continuous sandstorms. Some celestial bodies boast giant stars capable of swallowing entire planetary systems, while others, millions of light years away, exhibit structures resembling jellyfish galaxies. The exploration invites us on a fantastic journey to encounter these incredible cosmic wonders. Embarking on a space journey beyond our solar system involves the challenge of selecting a planet that closely resembles Earth from thousands of candidates. The Earth Similarity Index, ESI, emerges as a crucial tool, considering parameters such as radius, density, and average surface temperature. This index aids in estimating mass, chemical composition, gravitational level, atmosphere presence, and the potential for liquid water. However, a high ESI doesn't guarantee favorable conditions for life, as various factors, including weak magnetic fields and proximity to parent stars, impact habitability. Categorizing celestial bodies based on their ESI reveals 3 groups. The first includes objects with ESI under 0.5, predominantly gas giants or extreme temperature entities. The second comprises objects with ESI between 0.5 to 0.7, showing a closer resemblance to Earth. The third category consists of objects with ESI over 0.7, potentially harboring conditions conducive to life. Notably, an exoplanet named T-Garden b, located 12.5 light-years away, stands out with a remarkable ESI of 0.95, only 0.05 less than Earth's ideal value. Teegarden b, orbiting a small red dwarf star, lies within the habitable zone and completes an orbit every 5 days. While it receives 15% more radiation than Earth from the Sun, its surface temperature remains too low for life sustenance. However, the possibility of hidden oceans under ice remains. As exploration continues, mysteries of these celestial bodies promise to unveil new wonders, reinforcing the continuous pursuit of understanding the vast universe that surrounds us. And silicate mantle is believed to be at the core of the planet. The outer part of this celestial object is covered by a relatively thin crust composed of solidified rocks. Mathematical modeling indicates that the average temperature on Teegarden b is 28 degrees Celsius, which is 14 degrees Celsius higher than that of Earth. This suggests that the surface conditions on the planet are conducive to the existence and retention of liquid water, making it potentially favorable for various microorganisms. Despite Teegarden b being massive and capable of maintaining a comparatively dense atmosphere, the radial velocities method, employed for exoplanet detection, is insufficient for gathering information about the atmosphere's composition. It is essential to recognize that a planet's temperature profile is directly influenced by its atmosphere's composition. For instance, a dense atmosphere with high levels of methane and carbon dioxide can result in a strong greenhouse effect, while dense clouds of water vapor may reflect sunlight, reducing temperatures. However, Teegarden b is not without flaws. Its close proximity to its parent star implies that it is tidally locked, always facing the star with one side, causing significant temperature differences between the illuminated side and the shadowed side. Teegarden's star, being a red dwarf, is prone to sudden flares, with fluctuations in luminosity reaching up to 30%, significantly impacting nearby planets. Despite these challenges, the planet's potential for sustaining life remains high, given the remarkable adaptability and resilience often exhibited by biological organisms. The unique characteristics of Teegarden b highlight the fascination with potentially habitable planets featuring moderate climates. Amid the vast diversity of celestial bodies, those with conditions suitable for life draw particular attention. On the other hand, there exists a category of anomalous celestial objects displaying unusual behavior, challenging scientific understanding and warranting special attention. One such anomalous world is found in the Kepler 413 system, where an unknown object transiently reduces the luminosity of a distant star during a standard exoplanet transit. The initial assumption of a typical exoplanet discovery is challenged when the expected second transit does not occur 180 days later. However, the mysterious object reappears 800 days later, unveiling a highly unusual orbit. Kepler 413 bits, a cool giant, orbits a binary star system and experiences gravitational perturbations, causing cyclic oscillations in its orbit and actual rotation. The eccentric orbit, combined with periodic shifts, leads to bizarre changes in climatic conditions on Kepler 413 bits' surface, the region receiving the most light shifts between the equator and poles, resulting in dramatic temperature variations. The planet's unique orbit generates massive planetary-scale hurricanes, potentially larger than Jupiter's Great Red Spot. Ice clouds propelled by air currents and atmospheric emissions may further contribute to the planet's dynamic and harsh conditions. Moving on to another peculiar celestial object, approximately 190 light-years away in the HD 10606 system, a gas giant orbits a yellow dwarf with an exceptionally variable climate. The gas giant rushes toward its parent star, experiencing significant temperature increases within a short period. This leads to the formation of violent hurricanes and shock waves, generating atmospheric expansions and contractions. The extreme changes in conditions on HD 10606 bits make it a challenging place to exist. However, it may seem serene when compared to the world found 530 light-years away in the Kepler 36 system. This system contains a yellow subgiant orbited by 2 planets, a rocky super-Earth, and a hot mini-Neptune. The planets approach each other closely every 97 days, causing gravitational interactions that result in cataclysmic events on the rocky planet's surface. The intense forces at play lead to earthquakes and volcanic eruptions, with some regions of the planet potentially experiencing constant geological activity. In the vast expanse of space, These anomalous celestial objects showcase the diverse and dynamic nature of the cosmos. While some planets offer potential habitats for life, others present extreme and enigmatic conditions, challenging our scientific understanding and beckoning further exploration and study. The tranquility of creating seas with perpetually bubbling red-hot magma adds an enigmatic touch to a peculiar celestial system. The formation of such an unusual system remains a topic of debate. Kepler-36b, aptly dubbed the Super-Earth, orbits its parent star at a distance of 12 astronomical units, completing a full orbit in 14 days. This massive celestial body, with a mass 3.8 times that of Earth and a radius 1.5 times larger, exhibits a temperature of 980 K, over 700 degrees Celsius, and an average density approximately 30% higher than Earth's. Calculations suggest Kepler-36b could be a Thean planet, a gas giant's core stripped of its atmosphere, rich in heavy metals, sulfur, and silicon compounds. Accompanying Kepler-36b is its gravitational counterpart, Kepler-36c, likely classified as a hot mini-Neptune, orbiting in a nearly circular path with a radius of 0.13 astronomical units. It completes an orbit every 16 days. Kepler-36c boasts a mass 7 times that of Earth and a radius 3.7 times larger. Its proximity to the star results in a high temperature of 928 K, 65 degrees Celsius. The celestial body is expected to possess a thick, layered atmosphere primarily composed of nitrogen, hydrogen, and helium, potentially evolving into a supercritical fluid surrounding a solid core. The dynamics of the system, influenced by mutual gravitational forces, induce chaotic and unpredictable behavior. Mathematical modeling indicates a 91% probability of a collision between the two planets within the next 70 million years, leading to the generation of hundreds of thousands of debris pieces. The resulting dispersion of debris throughout the planetary system amplifies chaos, making predictions about the system's evolution challenging. Moving to a system 434 light-years from Earth, an intriguing object known as Super Saturn orbits a young sun-like star at 4 astronomical units. This brown dwarf, or large gas giant, is approximately 20 times the mass of Jupiter and is considered a young planet, still in the process of formation. Its atmosphere, rich in hydrogen and helium, encompasses a massive metallic core. The system of rings around Super Saturn, akin to those of Saturn but much larger, exhibits randomness, and their total mass surpasses that of Earth. Observations suggest the existence of exosatellites, with one potentially clearing its orbit, creating a rupture in the ring structure. 2 additional celestial bodies, each with approximately 30% of Earth's mass, are also detected in the system. Simulations, factoring in radiation from the parent star, heat flow from the gas giant, and tidal influences, paint a complex picture. Despite the potential for comfortable temperatures on exosatellites, the system's dynamics contribute to multiple eruptions on the satellite's surface, creating a unique climatic zone between land and the ocean floor. However, the instability of such structures raises questions about their long-term appearance. Shifting focus to rogue planets, celestial objects drifting freely in stellar space. These enigmatic bodies have been challenging to detect due to their limited thermal and light energy emissions. The concept of rogue planets has been supported by advancements in observation equipment, revealing potential candidates numbering over 24. The Milky Way itself might host up to 100 billion of these free-floating planets, marking the beginning of discoveries in this field. One of the confirmed rogue planets, Y855 to 714, lies 7.27 light-years away from the Sun. Discovered in 2014 with the WISI Orbital Infrared Telescope, this celestial body emits no visible light due to its extremely low temperature ranging from 225 to 260 Kelvin, -48 to -13 degrees Celsius. Resembling a cooled-off gas giant, it is predominantly composed of hydrogen. Observations in 2016 indicated the presence of significant water amounts in its atmosphere, forming ice particle clouds. 2 proposed scenarios for the origin of rogue planets involve their ejection from a regular planetary system's protoplanetary disk or expulsion due to gravitational interactions or collisions within the planetary system. The mysteries surrounding these celestial wanderers are slowly unraveling, with technological advancements providing new insights into their characteristics and origins. The likelihood of events like those mentioned in another system is admittedly relatively small. According to an alternate version, the space object in question might have originated like any other star, formed through the compression of interstellar gas. However, its mass proved insufficient to trigger thermonuclear reactions in its interior, limiting it to a potential state as a gas giant or a brown dwarf, not a rocky planet like Earth. Some researchers propose classifying these objects as sub-brown dwarfs, while others advocate using the term PEL, planetary mass object, for interstellar wanderers lacking thermonuclear activity. Current knowledge suggests that WISE 855-714 has a mass ranging from 3 to 10 Jupiter masses, insufficient for thermonuclear reactions but adequate to retain internal heat. Considering our understanding of natural laws, predictions about the conditions on the celestial body's surface can be made. Gas giants resembling Jupiter, according to research by David John Stevenson from the University of California, don't rapidly cool off after moving away from their stars. The thick hydrogen atmosphere provides reliable thermal isolation, while the hot nucleus made of metallic hydrogen can sustain the planet's heat. Estimated temperatures suggest that the lower strata of the hypothetical celestial object's atmosphere could support liquid water, potentially in the form of giant clouds of tiny droplets. Mathematical modeling of WISE 855-714 by scientists from the University of Edinburgh indicates a likely surface temperature of 250 K or -23 degrees Celsius. The atmosphere includes a relatively warm layer, about 100 kilometers thick, comparable to Earth's conditions, creating a potentially favorable environment for organic life. Rogue planets, though not necessarily massive gas giants, challenge the freezing conditions of space. In 2020, a candidate for a rogue planet was detected using gravitational microlensing techniques, showcasing similarities to Earth's mass. If these objects formed in protoplanetary disks, they might have been ejected due to space cataclysms or gravitational interactions with larger neighbors, becoming free-floating planets. Their fate depends on factors such as atmospheric density and thermal isolation. If adequately dense, the atmosphere could keep the planet thermally isolated, potentially maintaining a liquid ocean with the chance of harboring primitive anaerobic life. Current knowledge about rogue planets primarily stems from mathematical modeling and complex calculations. The Cleopatra project, utilizing microlensing, aims to detect free-floating planets and define their parameters. This project, expected to launch in 2025, will involve an interplanetary spacecraft equipped with artificial intelligence to process and analyze collected information. The Cleopatra project promises exciting and significant discoveries in the realm of rogue planets. The fate of these solitary worlds in the universe's dark depths remains uncertain. While there is a minimal chance for an orphan planet to be captured by a star's gravitational field and become part of a planetary system, most are destined to drift through space for millions or billions of years, eventually succumbing to black holes or catastrophic events, taking their secrets with them. In 2003, routine observations of the starry sky led to the discovery of a small yellow dwarf in the Phoenix constellation, later named WSP-96. In 2013, the Super WSP Orbital Telescope identified an extremely rarefied gas giant near the star. Initial spectral analysis revealed an atmosphere transparent and nearly devoid of water vapor. In 2022, James Webb, a new generation orbital telescope, reanalyzed the object's atmosphere, contradicting previous estimates. The data conflict prompted questions about our understanding of the universe. The James Webb Space Telescope, initiated in 1996, took 25 years to develop and modernize. Launched to a destination 1.5 million km from Earth, it mitigates interference from Earth's, Moon's, and Sun's radiation with a multi-layer heat-reflecting screen. Despite challenges, the telescope's unparalleled sensitivity allowed it to make significant discoveries, raising both expected and unexpected questions. One study with a paradoxical outcome involved the spectral analysis of WSP-96 bits, an exoplanet with extremely low density. Located 0.45 astronomical units from its parent star, it completes an orbit in just 3.5 days. James Webb's spectral analysis contradicted earlier observations, revealing the presence of thick clouds, contrary to initial transparency. The telescope's discoveries, from the expected to the surprising, showcase its capability to unveil the mysteries of the cosmos. The calculations indicate that the celestial body's mass is half that of Jupiter, with a diameter 20% larger than Jupiter's. Due to its extreme proximity to the star, the outer layers of the object reach a high temperature of 1,285 K or just over 1,000 degrees Celsius, categorizing it as a hot Jupiter. Such planets are known for significant atmospheric losses due to stellar wind. Previous measurements of WSP-96 bits showed clear sodium lines in its atmosphere, interpreted as a sign of an exceptionally clean and cloudless atmosphere. However, James Webb's information revealed a different reality. The gas giant's outer layers contain substantial amounts of water vapor, potentially forming a large haze or thick clouds, reflecting light. This discrepancy raises questions about the accuracy of earlier studies and the need for further detailed exploration of WSP-96 bits. James Webb's discoveries extend beyond WSP-96 bits. A unique system of 3 brown dwarfs located 69 light-years away presents an intriguing cosmic configuration. Brown dwarfs too large to be planets and too small to sustain stable thermonuclear reactions are challenging to detect due to low surface radiation. However, James Webb's infrared capabilities enable the observation of objects otherwise invisible in the optical range. The 2 larger components of the system closely resembled each other, with a distance of approximately 2 astronomical units between them and a total mass slightly over 100 times that of Jupiter. Both objects exhibit relatively high temperatures of around 2,600 Kelvin. The third component, situated at a greater distance of about 100 astronomical units, possesses a mass between 14 and 23 Jupiter masses, with a radius 20% larger than Jupiter. Despite being colder with outer layers at 1,240 K, this brown dwarf is notably warmer than gas giants in our solar system. Surprisingly, its outer layers contain not only common components like water, methane, or carbon dioxide, but also minute particles of various silicon compounds, possibly forming vast clouds. The separation of these brown dwarfs may be attributed to a gravitational influence, and the existence of silicon clusters supports theoretical predictions. James Webb's capabilities extend to observing vast space structures, such as the Kina Nebula, one of the largest stellar nurseries in our galaxy. Located about 8,500 light-years away, the nebula contains giant clouds of interstellar gas and dust, along with thousands of stars, including notable objects like Ea Carini and Delaware 25. Infrared cameras on James Webb can unveil stars within dusty hazes, contributing to the discovery of previously unknown stars. The Kina Nebula serves as a prolific area for star formation, allowing astronomers to observe thousands of protostars and young stars in various stages of evolution within the same gas cloud. This comprehensive observation aids researchers in understanding the complex and lengthy process of star formation, shedding light on forces involved in the birth of new stars. Furthermore, James Webb's sophisticated instruments, including an 18-section mirror and high-precision tools, enable the capture of light from objects at the very edge of the visible universe, more than 13 billion years old. Gravitational lensing, a rare and fortunate occurrence, amplifies light from distant objects, making them visible. Observing the galaxy cluster SMX 723, James Webb captured light from a distant and ancient galaxy, estimated to be 13 billion years old, passing through gravitational lenses 3 times. The amplification, around 20 times, allowed astronomers to distinguish the object from background noise. This discovery includes about 10 other star clusters with complex structures, offering insights into the early stages of the universe's evolution and potentially challenging existing notions of its age. In conclusion, James Webb's profound observations continue to unravel mysteries in the cosmos, from individual celestial bodies like WSP-96 bits to extensive structures like the Kina Nebula and ancient galaxies, pushing the boundaries of our understanding of the universe's intricacies. Some planets are engulfed by oceans of molten lava, while others are encased in a permanent shell of ice. Diverse planetary compositions exist, ranging from entirely oceanic surfaces with no dry land to atmospheres filled with sulfuric acid rains or occurrences of diamond snow. The discovery of such worlds involves various techniques, as direct observation through a telescope is usually impractical. In 2009, Kepler, the first space telescope designed explicitly for locating planets beyond the solar system, was launched. Equipped with 42 charge-coupled devices, CCDs, boasting a total resolution of around 96 megapixels, Kepler, in its 3.5 years of active operation, identified over 3,500 exoplanet candidates with 2,000 confirmations through repeated observations. The transit method, based on the observation of a star's luminosity decrease when a planet passes between the star and the observer, was utilized by Kepler. Despite Kepler's success, its remote and dim discoveries often lack the detail necessary for thorough examination. The Transiting Exoplanet Survey Satellite, TSS, launched in 2018, succeeded Kepler, focusing on searching for rocky exoplanets around the brightest stars within 200 light-years from the Sun. TESS employs the same transit method, equipped with 4 refractors, a 24x24 deg field of view, and 10 centimeters aperture. One of TESS's notable discoveries is TOI 700d, a rocky exoplanet comparable in size to Earth, located in the habitable zone of its host star, TOI 700, a red dwarf. TOI 700d takes 37.4 days to complete an orbit, lying along the inner edge of the habitable zone. While its precise mass remains undetermined, estimates suggest it may range from 1 to 3 times that of Earth. The potential for liquid water on its surface and a steady-state temperature of 268.2 K make TOI 700 intriguing. Although tidally locked to its star, it may experience short, unfavorable periods when it comes too close to its star. The presence of living organisms on TOI 700 raises the possibility of adaptation to harsh conditions or migration to more favorable areas. While TESS has completed its main mission, it continues its operation, capturing images of the sky, including the Milky Way plane. Over 2,100 exoplanet candidates have been discovered, with ongoing observations. Some of the most terrifying exoplanets, such as the extremely dark gas giant TRAPPIST-1b, absorb over 99% of light due to unique surface properties. The chemical composition of its surface, causing this extreme darkness, remains a mystery, hinting at potential undiscovered chemical reactions. In summary, the exploration of exoplanets reveals a diverse array of planetary compositions and environments. From molten lava to icy shells, each planet presents unique characteristics. Discovered through sophisticated telescopes like Kepler and TSS, ongoing observations continue to unveil the mysteries of these distant worlds, expanding our understanding of the vast and varied cosmos. 2b possesses a mass of 1.2 Jupiter masses and a radius 1.27 times that of Jupiter. Despite its scorching atmosphere reaching temperatures of 1,000 degrees Celsius, giving it a faint red glow, it doesn't hold the title of the most dangerous place in the universe. Numerous objects in space are more terrifying. Consider 55 Cancri, found in the system of a Sun-like star. 55 Cancri A, discovered on August 30, 2004, using Doppler spectroscopy. It boasts a mass around 8 Earth masses and a radius 1.875 times that of Earth. Tidally locked, one side always faces the star, reaching temperatures of 2,400 degrees Celsius on the day side and 1,300 degrees Celsius on the night side due to its close distance of 0.183 astronomical units from its parent star. Volcanism causes dust clouds, trapping heat and preventing it from escaping. The atmosphere includes helium, hydrogen, and large amounts of carbon, potentially forming layers of graphite and diamonds. Moving to PSR 1257 plus 12c, an exoplanet in a pulsar system located 0.36 astronomical units from the system center, 2,300 light-years away. With a mass 4 times that of Earth, it orbits in 66 days, and its survival suggests post-supernova formation. While potentially hazardous due to pulsar radiation, it doesn't claim the title of the most dangerous. Kepler 70 Bits, the hottest exoplanet known, orbits the sub-dwarf star Kepler 70 with a surface temperature of 6,800 degrees Celsius, 0.44 Earth masses, and a 0.76 Earth radius. With a day less than 6 hours long, it regularly passes Kepler 70c at 240,000 kilometers, the closest known planetary pass. However, its potential origin as part of its parent star raises questions about its exoplanet status. WSP 12 bits, located 87 light-years away, with a radius 1.93 times that of Jupiter and a mass of 1.46 Jupiter masses, orbits its parent star at 0.03 astronomical units. With temperatures soaring to 2,200 degrees Celsius, the star's gravitational pull is gradually absorbing the exoplanet, expected to be destroyed in about 10 million years. While close, it doesn't top the list of dangerous exoplanets. Delving into the atmosphere of HD 189,733 bits reveals a hazardous environment with winds reaching 8,700 kmph, carrying silicate particles and glass precipitation. Despite its Earth-like appearance, the surface poses life-threatening dangers. It is a bright blue gas giant with a 1.1 times Jupiter's diameter, 113% Jupiter's mass, and a close proximity of 5 million km to its star, resulting in extreme temperatures of around 930 degrees Celsius on the day side. The first theoretical inklings of ocean worlds surfaced in the 1970s, suggesting planets covered in water due to radioactive decay and tidal forces. These processes may occur on Jupiter's and Saturn's moons, but their distance from the Sun keeps them icebound. As research continues, these unique worlds challenge our understanding of planetary environments and serve as a reminder of Earth's exceptional conditions. The term ocean planet refers to a type of celestial body where the surface ocean is not concealed by ice, and its depth exceeds 100 kilometers. In 2004, French astrophysicists, led by Christophe Satan, conducted theoretical calculations on the formation and evolution of these planets. If the forming planet's mass exceeds 10 times that of Earth, it attracts hydrogen and helium from the surrounding gas and dust cloud, evolving into a gas giant. On the other hand, a planet with a mass of 6 to 8 Earth masses would consist of ice and rocks in roughly equal proportions. The orbit's distance from the host star determines whether it becomes an ice giant or a cold super-Earth. In 2009, an exoplanet named GJ 1214 bits was discovered near a dim star 42 light-years from Earth, with a diameter 2.5 times that of Earth and 6.5 times its mass. It has an estimated average density suggesting it is 75% water or water ice and 25% rock. Proximity to its host star results in scorching surface temperatures. Spectroscopic investigations of its atmosphere hint at predominantly water vapor with some ambiguous results. GJ 1214 bits' conditions resemble those inside a giant steam boiler, with a blurred border between the ocean and atmosphere due to thermodynamic equilibrium. Exploring ocean planets is scientifically intriguing, and NASA estimates billions of such planets may exist in our galaxy. These planets can be cold, harboring an ocean under an ice shell, or warm like GJ 1214 bits. Water, being a widespread compound in the universe, enhances the chances of discovering new ocean planets. Stellar nurseries, where stars are born, are scattered across the galaxy, ranging from modest to expansive sizes. The Orion Nebula, located 1,344 light-years away, is one of the best-studied stellar nurseries. Trapezium, an open star cluster within the nebula, includes stars with masses ranging from 15 to 40 solar masses, illuminating the surrounding area. Theta 1 Orionis C is the most massive and brightest star in the cluster. Further exploration reveals Theta 2 Orionis, a system of 3 gravitationally bound stars near the Orion Bar. The James Webb Space Telescope has enabled detailed observations of the Orion Nebula, unveiling around 180 protoplanetary disks, known as props. One such prop, Orion 29468-6, is expected to evolve into a system with several exoplanets and satellites, creating a stunning celestial display in its night sky. The central region of the nebula is filled with ionized hydrogen, absorbing high-energy stellar radiation and exhibiting varying temperatures and pressures. Studying these cosmic phenomena enhances our understanding of planetary formation, stellar evolution, and the dynamic interplay within stellar nurseries. In various regions of the nebula, currents and vortices can attain speeds up to 50 km/s, with sizes surpassing that of the solar system. Certain areas exhibit thin strands, extending for several light years, composed of relatively cool molecular hydrogen, devoid of methane, ethane, and water. Moving outward, the central region of the Orion Nebula is shrouded in a vast cloud of cooler, denser gas. The interplay of the cloud of bright stars and ionized hydrogen generates a beautiful multicolored curtain of light, concealing hundreds of space objects, detectable through the infrared cameras of contemporary telescopes. By amalgamating data from various sources, astronomers have identified approximately 700 protostars in different stages of evolution within this region. The concentration of these objects is lower than in the central part of the nebula due to the lesser gravitational compression of interstellar gas. Most of these protostars are young by cosmic standards, still in the process of formation. According to modern concepts of stellar evolution, new stars emerge through the gradual gravitational compression of large clouds of interstellar gas. As a result, giant nebulae fragment into closely grouped gravity centers, evolving into protostars. These clusters, known as stellar nurseries, reach temporary equilibrium when the internal pressure of the compressed gas offsets gravitational forces. The remaining material forms a swirling vortex disk, with some absorbed by the future star and the rest expelled beyond the nascent system. The magnetic field of the growing star contributes to this process, creating flows that generate large-scale vortices and hemispheres termed Herbig-Haro objects. These objects exhibit various shapes and colors due to the dissipation of kinetic energy into light and heat. Stellar nurseries, hosting closely spaced protostars emitting gas emissions, give rise to a rich variety of Herbig-Haro objects. These objects are highly unstable, rapidly changing color and shape, dispersing completely over tens of thousands of years. The shock waves they produce are observable by telescopes. One intriguing variety of this phenomenon is the bullets, hundreds of astronomical units in diameter, detected in the Orion Nebula. Moving at incredible speeds, these bullets penetrate thinner hydrogen clouds, creating far-reaching shock waves. Spectral analysis indicates the presence of iron atoms in the frontal parts of these objects, glowing in the infrared. Their origin, estimated at about 1,000 years old, remains a mystery. The Orion Nebula is part of a more extensive cosmic structure called the Orion Cloud, stretching for hundreds of light years and virtually comprising the entire Orion constellation. Adjacent to the Orion Nebula is the B Loop, an emission nebula created around 3 million years ago by consecutive supernova explosions. Despite its beauty, the Orion Nebula is fragile and constantly evolving. Stellar winds, pressure from young stars, gas emissions, and turbulent vortices disperse its material into surrounding space. Over time, it has lost approximately 60% of its original material, and in about 100,000 years, it will be stripped of its remnants, leaving behind an open star cluster. Moving on to a celestial object 202 light-years from Earth, known as K2141 bits. It orbits an orange dwarf star, K2141, at a distance of 0.007 astronomical units. This rocky exoplanet, 5 times more massive than Earth, has a radius 1.5 times that of our planet. With an extremely close orbit, it is tidally locked to its star, resulting in scorching temperatures on its day side, reaching 3,270 K or 3,000 degrees Celsius. The atmosphere is speculated to consist of heavy metals and silicates, creating an exotic composition. The night side experiences freezing temperatures, generating strong winds and potentially forming fiery rain and lava rivers. Comparatively, K2141 bits is not the hottest planet known. Healt, 9 bits, located 670 light-years away, has a surface temperature of 4,600 K or 4,330 degrees Celsius, making it one of the hottest known exoplanets. Orbiting a whitish blue star, KELT-9, the gas giant KELT-9 bits has a mass 2.8 times that of Jupiter and completes an orbit around its parent star every 1.5 days. Its proximity and extreme temperature cause it to lose its atmosphere gradually due to the star's powerful stellar wind. V391 Pegasi b, situated 4,570 light-years away, orbits a white dwarf star, V391 Pegasi. The planet, a gas giant 3 times the mass of Jupiter, survived the shedding of its progenitor star's outer layers. During the star's transformation into a red giant, the rarefied outer layers barely affected the planet's orbit, allowing it to remain intact for a while. V391 Pegasi b's parameters changed dramatically due to the host star's collapse, making it challenging to discern its original state. In the vicinity of a small star known as 391 Pegasi, 4,570 light-years from Earth, orbits an intriguing celestial object named 391 Pegasi b. This gas giant, 3 times the mass of Jupiter, experienced a remarkable fate as its progenitor star transformed into a white dwarf. Despite the challenges in understanding its original state, the survival of 391 Pegasi b within the tumultuous environment of its dying star offers a unique perspective on the cosmic interactions between planets and their parent stars. As we explore the vastness of space, we encounter pulsars, neutron stars spinning at extraordinary speeds, with distinctive fast and regular pulsations detectable at radio wavelengths. These celestial objects, nearly invisible through regular telescopes, illuminate the cosmic landscape in a different spectrum. In particular, pulsar neutron stars exhibit unique spectra due to their rapid and rhythmic pulsations. These objects serve as fascinating examples of the diverse astronomical entities concealed within the depths of the universe. The next celestial object of interest is a pulsar located around 4,000 light-years away from Earth. This neutron star, with a diameter of just 20 kilometers and a mass approximately 1.4 times that of the Sun, spins at an incredible rate of around 10,000 rotations per minute. Emitting powerful electromagnetic radiation impulses, this pulsar poses a hostile environment for the exoplanet that orbits it. The exoplanet completes a full orbit in just 2 hours, maintaining a distance from the pulsar smaller than the Sun's radius, approximately 600,000 kilometers or 0.004 astronomical units. With a mass around 330 times that of Earth and a radius 4 times larger, the exoplanet experiences gravity on its surface that is 20 times stronger than on Earth. Its average density is estimated to be about 23 grams per cubic cm, higher than that of most chemical compounds known. The composition of the planet includes crystallized carbon under pressure, and its upper layers contain oxygen, likely chemically bound with carbon. While it seems improbable that a celestial body located so close to a star could have survived a supernova event, it is more plausible to assume that the exoplanet formed after the progenitor star's life cycle ended and transformed into a pulsar. This celestial object remains one of the most dangerous and hostile in the cosmos. Moving 650 light-years away from Earth, we encounter IRC plus 10,216, a majestic star also known as Eta Leonis. At its pulsation peak, this star's radius may reach 560 times that of the Sun, approximately 2.6 times the distance from Earth to our parent star. With a mass of about 1.5 to 4 solar masses and a surface temperature of 2,300 K or 2,000 degrees Celsius, Eta Leonis emits, on average, 8.5 thousand times more energy than our Sun. As a red giant in its final life stage, Eta Leonis has an estimated age of several billion years. The star's transformation into a red giant involves the expansion of its inner pressure, leading to increased proportions, more rarefied and unstable outer layers, and a change in color to a blood red hue. The star undergoes thermonuclear reactions in its depths, causing an increase in pressure and temperature, resulting in a chain reaction of nuclear fusion. This process, known as the helium flash, dramatically transforms the star's inner structure, leading to changes in luminosity. Eta Leonis has a pulsation cycle of 649 days, with its luminosity at its peak being 11,300 times brighter than the Sun. The star loses material at a rate of 4*10^22 tons per year, forming a carbon-oxygen gas nebula around it. The nebula, with an elaborate structure, contains around 70 different chemical compounds, including carbon dioxide, water, and ammonia. Eta Leonis may have had planets in the past, but observations suggest that they were likely swallowed up during the star's expansion. Subtle changes in the star's orbit were detected, possibly indicating the presence of a small red dwarf in its vicinity. Exploring the mysteries of the universe, we come across the unique process of stellar evolution. Stars with incredibly high temperatures in their interiors are sources of energy due to thermonuclear synthesis. The primary process involves the fusion of hydrogen and helium, releasing significant energy. As a star depletes its hydrogen supply, it expands, cools off, and transforms into a red giant. Eventually, red giants become unstable, shedding their outer layers in a supernova event. The remnants form a white dwarf, gradually cooling off over billions of years. This transformation generates new elements, such as uranium, gold, or lead, contributing to the creation of new celestial objects. Radioactive decay on these planets can lead to the heating of their interiors, melting ice, and creating conditions for the genesis of life. Intriguingly, when stars have a mass higher than a certain value, heavy thermonuclear synthesis can become the main energy source even after hydrogen depletion. These stars are known as Wolf-Rayet stars, discovered in 1867 by Charles Wolf and George Rayet. These heavy hydrogen-depleted stars are in the final stages of their evolution, with only a few hundred discovered in our galaxy. They are categorized into three main sequences based on the prevalent element in their spectra: nitrogen, carbon, and oxygen sequences. W102, discovered in 1971, falls into the oxygen spectral sequence, making it one of the hottest stars studied. This star is characterized by unusually bright oxygen lines in its radiation spectrum. As we delve into the depths of space, we witness the incredible processes shaping the cosmos. Each celestial object tells a unique story of its evolution, from the intense heat of stellar interiors to the formation of new elements and the potential for life in the distant future. The universe, constantly evolving and undergoing global cataclysms, ultimately reveals fresh rays of light at the end of every storm. The star WR102 exhibits an exceptionally high surface temperature, surpassing 210,000 Kelvin, making it approximately 36 times hotter than our Sun. Its luminosity is extraordinary, estimated at over 380,000 times that of the Sun. Situated around 10,000 light-years away in the Sagittarius constellation, WR102 belongs to the rare Wolf-Rayet star class W2. This class is characterized by a high abundance of oxygen and minimal hydrogen, relying on heavy cores of elements like neon, carbon, and oxygen for energy. Only 9 such stars have been discovered to date, with WR102 being one of them. Oxygen spectral sequence stars are rare due to the scarcity of Wolf-Rayet stars, requiring a minimum mass of 40 solar masses, and because this class represents the final stage of evolution for such stars, lasting from a few thousand to 10,000 years. Despite its modest dimensions, WR102 has a high density, with a radius measuring 58% that of the Sun and an estimated mass of 15 to 18 solar masses. Intense chemical reactions and a powerful stellar wind, with particles reaching over 5,000 km/s, cause WR102 to lose material rapidly. The star is expected to go supernova in the next 1,500 years, potentially already having occurred due to its distance of 10,000 light-years from Earth. WR102 lacks orbiting planets, but is enveloped in a gas cloud exposed to ultraviolet radiation and a strong stellar wind, creating an elaborate structure of protuberances and arches. The gas cloud may be remnants of the star's former hydrogen outer layer or formed by particle flow emitted by the star. WR102 is not the only intensely hot place in the universe. Other stars like W142, W30A, W93b, and the central star in the Bug Nebula NGC 6302 are also around 200,000 Kelvin. Neutron stars, born with temperatures reaching 100 billion Kelvin, cool off with active neutrino emissions. The surface temperature of neutron stars is never less than a few hundred Kelvin, and the ultimate temperature record in the universe is estimated to be around 1.4*1032 Kelvin, the Planck temperature at the moment of the hypothetical Big Bang. Considering WR102's data in the context of stellar evolution, the star is in its autumn years. Unlike main sequence stars, Wolf-Rayet stars do not expand in their final stages. Their substantial mass holds them together. However, Bedadar 102's intense stellar wind and mass loss may lead to destabilization, indicating its readiness to go supernova in the next 1,500 years. A supernova event would be accompanied by an extra-powerful gamma-ray flare, but the Earth is too far away to experience significant effects. After going supernova, Bedadar 102 will lead heavy chemical elements, lead and iron, and undergo processes of proton and neutron capture, forming still heavier elements. The remnants will either become a neutron star or a black hole. The ejected outer layers will form a nebula that slowly cools off. Many billions of years later, this material could form a new planetary system. Previously, Uae was considered the largest known star, located 9,500 light-years away and covering areas beyond Jupiter's orbit. However, Stephenson 2-18, part of the open cluster Stephenson 2, now claims the title of the largest star in the known universe. Situated approximately 20,000 light-years away in the Scutum constellation, Stephenson 2-18 has a radius that may reach up to 1.2 billion km, 10 times the distance from Earth to the Sun. Its volume is estimated to be about 10 billion times that of the Sun. Stephenson 2-18's luminosity is 440,000 times that of the Sun, with a surface temperature of about 3,200 Kelvin, falling into the red band of the light spectrum, categorizing it as a red supergiant. Despite its impressive size and luminosity, Stephenson 2-18 cannot be seen with the naked eye due to its low surface temperature and shrouding clouds of stardust and gas. The mass of Stephenson 2-18 remains ungauged, but assuming it is similar to Uae and other supergiants, it should be within 20 solar masses. The low average density of supergiants like Stephenson 2-18 is almost equal to the density of the Earth's atmosphere at a height of about 90 kilometers above sea level. These supergiants sustain thermonuclear energy even with such low densities. Stephenson 2-18's habitable zone is expected to be vast, with a middle lying approximately 663 astronomical units away from the star's center, equivalent to 20 times the distance from the Sun to Pluto's orbit. The habitable zone area is anticipated to be 1 billion times that of the Sun. While the existence of planetary systems around supergiants is possible, the short lifespan and unstable conditions of these stars make the chances almost negligible. No confirmed exoplanets have been discovered in the vicinity of Stephenson 2-18. Observing the universe, people once considered the Milky Way a path of gods, but scientific progress eventually revealed it as the collective light of billions of stars too distant to distinguish individually. Emmanuel C. suggested the idea of stars forming part of a single structure of enormous dimensions in 1755, anticipating the concept of galaxies. It wasn't until the early 20th century that observations confirmed the existence of other galaxies, with Edwin Hubble devising a classification system in 1936. The Milky Way is categorized as a barred spiral galaxy. As technology advanced, the true appearance of the Milky Way emerged. It is an old galaxy, with stars in its central globular cluster being among the oldest objects in the universe. Light emitted by stars in the Milky Way takes thousands of years to reach Earth, providing a glimpse into the past. The fascinating phenomenon of the Milky Way, once shrouded in legends, is now understood as the collective glow of distant stars. Clusters emerged approximately 13 billion years ago, and within the Milky Way, new stars continue to be actively born. The galaxy is vast, with a disk diameter of around 200,000 light-years and an even more extensive halo, housing at least 200 billion stars, 25 to 100 billion brown dwarfs, over 1 trillion planets, and various celestial objects. The Milky Way also contains vast clouds of cosmic dust and interstellar gas. Strikingly, about 90% of its overall mass is composed of dark matter, a mysterious substance with negligible light emission but significant gravitational influence. By studying the trajectories of stars around the galactic center, scientists estimate the Milky Way's mass to be between 8 to 1.5 trillion solar masses. The central region of the Milky Way, shrouded in massive clouds of gas and dust, harbors a supermassive black hole known as Sagittarius A*, with a mass of 4.3 million solar masses. Advances in observation technology allowed the first image of this black hole to be captured in 2022. Within 3 light-years from Sagittarius at Asterisk, over 6,000 stars have been detected, including the fast-moving white-blue star S62. As we traverse the galactic center, we encounter large star clusters, and further away, another massive black hole with a potential mass of around 100,000 times that of the Sun. Moving outward, we reach the central molecular cloud, a hub of stellar nurseries, gas nebulae, and remnants of supernovae. Encompassing the galactic center is a bulge, an elliptical structure extending 10,000 light-years in length with a total mass of approximately 10 billion solar masses. The bar, stretching for 13,000 light-years, serves as the base for the Milky Way's spiral arms, one of which hosts the massive star cluster Stephenson Tube of 18. Beyond the galactic center, we explore the thin and thick components of the galactic disk. The thin disk, comprising 80% of the galaxy's visible mass, has a visible radius of 50,000 light-years, while the thick disk, 4 times as thick, is more rarefied and consists of old stars. Mathematical modeling suggests that the Milky Way may have merged with a hypothetical galaxy, Enceladus, 11 to 8 billion years ago, contributing to the formation of the thick disk. The galactic arms, including the Scutum Centaurus arm, Perseus arm, Norma arm, and Carina Sagittarius arm, are areas of high star count and gas concentration, fostering a star formation rate 3 to 5 times higher than the galactic average. Stars within these arms often spend their initial years in open clusters. The Milky Way's habitable zone, a ring with a radius of 22 to 29,000 light-years, offers favorable conditions for the genesis of biological life. However, the dense stellar population in this region can destabilize exoplanet orbits and expose them to lethal radiation. Moving outward, we reach the galactic drift, a region filled with massive clouds of interstellar gas and dust, potentially serving as a stellar nursery. The Milky Way's most extensive component, the halo, spans up to 260,000 light-years from the galactic center. Comprising globular clusters and stellar streams, the halo contains old stars over 12 billion years of age. Stellar streams like the Sagittarius stream reveal the gravitational capture of stars from a dwarf satellite galaxy. The Milky Way's halo also contains vast amounts of gas and dark matter, contributing to the galaxy's stability. The dark halo, stretching up to 2 million light-years, remains a mystery detectable only through gravitational interaction. Exploring beyond the Milky Way, distances to other galaxies range from millions to billions of light-years due to cosmological expansion. The redshift phenomenon, caused by this expansion, influences the perceived age of distant objects. Some galaxies, like M86 in the Virgo cluster, exhibit blue shifts, indicating motion toward the Milky Way. M86's high speed through scattered gas results in the shedding of its interstellar matter, leaving long trails of warm ionized hydrogen. Observations of galaxies like M86 provide insights into galactic interactions, collisions, and the complexities of cosmic structures. The galaxy ES-137d1, located 227 million light-years away, presents a unique shape and weight, ranging from 5 to 14 billion solar masses. With its strikingly original appearance, ES-137d1 is distinct from galaxies like M86. Despite their differences, both galaxies exemplify the dynamism and vastness of the universe, showcasing the ongoing interplay of gravitational forces, mergers, and the formation of stellar structures. As we continue our cosmic journey, the exploration of galaxies unfolds as a fascinating pursuit, revealing the intricate tapestry of the universe from the birth of stars within the Milky Way to the interactions between distant galaxies millions of light-years away. Each celestial entity contributes to the ever-evolving narrative of cosmic evolution, offering glimpses into the complexities and wonders of the vast cosmic tapestry. SL-137-001, a young and luminous blue giant, is a member of the vast Abell 3627 galaxy cluster, hurtling toward its center at an astonishing speed of nearly 2,000 km/s. As this galaxy encounters interstellar gas pressure within the cluster, its own gas is expelled, creating tails that extend up to 260,000 light-years. Interestingly, the mass of interstellar gas in these regions surpasses that within the galaxy, leading to frequent starbursts. The ongoing stripping of interstellar gas diminishes the galaxy's lifespan, hindering new star formation and impacting the structure of its spiral arms and central bulge. Despite the challenges, the galaxy offers an opportunity to study dark matter and its interactions by observing the behavior of the gas streams left in its wake. In contrast, another galaxy experiences a baby boom, with approximately 4,000 stars born annually minus 400 times more than in the Milky Way. Located 12.2 billion light-years away, this galaxy provides insights into the early stages of the universe's evolution. The Sombrero Galaxy M104, situated 30 million light-years from the Sun, boasts a distinctive ring of dust and cold hydrogen where most young stars form. This galaxy's inner structure, resembling that of elliptical galaxies, hints at a past collision and merger of two galaxies. Additionally, the Sombrero Galaxy emits exceptionally powerful X-ray radiation from its center, likely originating from a supermassive black hole with a mass exceeding 1 billion solar masses. Concluding the cosmic tour is the Black-Eye Galaxy, M64, characterized by a dark band of cosmic dust concealing its center. Approximately 17 million light-years away, this galaxy features two well-defined parts: an inner disk with a bulge rotating opposite to the outer ring. The unique structure suggests a history of two smaller galaxies colliding and merging. Zooming out to our solar system, it comprises a single star in its main sequence stage, along with planets, satellites, and over 1 million small celestial bodies like asteroids and comets. Neptune, the farthest known planet, orbits at about 30 astronomical units. Beyond Neptune lies the far, far out object at 132 astronomical units, and the hypothesized Oort cloud extends up to 60,000 astronomical units, defining the outer limits influenced by the Sun's gravity. The solar system resides in the Orion Arm, a component of the Milky Way galaxy with an estimated 400 billion stars. The Milky Way, in turn, is part of the Local Group, a collection of over 50 galaxies, including Andromeda and Triangulum, expanding to the Virgo supercluster, housing over 30,000 galaxies. We find the Local Group as a mere component. Further exploration leads to the Laniakea supercluster, covering approximately 520 million light-years and containing structures like the Virgo supercluster and the Great Attractor. The Great Attractor, acting as the gravitational center for nearby objects, remains a mystery due to the Milky Way's obstruction. The universe's large-scale structure comprises filaments, walls, and voids, with structures like the Hercules Corona Borealis Great Wall spanning an incredible 10 billion light-years. The observable universe, expanding continuously, is a sphere with a diameter of about 93 billion light-years. Objects beyond this sphere become mutually unobservable over time due to the ongoing expansion. This conventional area is termed the meta-galaxy, and hypothetical extrametagallactic objects lie beyond its visible boundaries. The nature of these extrametagallactic objects remains unknown, as they are beyond current observational capabilities. Various hypotheses suggest the absence of conventional space, time, and physical laws in these regions. Some propose a more complex superstructure or a multidimensional space. In essence, our journey through the cosmos reveals the vast and intricate tapestry of the universe, from galaxies and clusters to superclusters and beyond. Each celestial object, with its unique features and mysteries, contributes to our understanding of the cosmos, offering glimpses into the evolution and complexity of the universe on various scales. The mind-boggling superstructure of the universe prompts contemplation on the anthropic principle, suggesting the existence of other worlds beyond the observable universe. In these alternate worlds, fundamental constants like the speed of light or electron charge could differ, aligning with the concept of a multiverse depicted as bubbles separated by impenetrable walls. Each universe within this framework possesses distinct physical laws, with some radical hypotheses even questioning the objective reality of our world. Some propose the universe as a highly advanced simulation by superbeings or civilizations beyond our comprehension. The vastness of space, seemingly infinite, adds an element of awe and fear, yet it is known that the universe is expanding. As this expansion continues, a distant future awaits where space objects will vanish, starting with galaxies, then stars, plunging the cosmos into eternal darkness. Ursula K. Le Guin's poetic reflection on darkness and stars underscores the cyclical nature of existence, from birth to death. Exploring the theories of the universe's genesis, the steady-state universe, claiming perpetual equilibrium, gave way to the widely accepted Big Bang theory. Formulated in the 1910s and 1920s, this theory, based on Albert Einstein's general theory of relativity, posits that the universe's destiny is intertwined with dark energy. While the universe's age is estimated at nearly 14 billion years, uncertainties surround the nature of dark energy, influencing the expansion's continuation or potential reversal. Two possible scenarios, the Big Rip and the Big Crunch, speculate on the universe's fate. The rate of expansion, proportional to distances between objects, may lead to an ever-increasing expansion or contraction. The Big Rip envisions an escalating expansion, tearing galaxies, stars, and matter apart until atoms and subatomic particles disperse. The Big Crunch scenario suggests gravitational forces exceeding expansion forces, culminating in a compressed singularity, reminiscent of the universe's birth. The fate of the universe hinges on our understanding of dark energy, which remains limited. Theories explore possibilities like the universe's rebirth through a big bounce, perpetuating cycles of big bangs and contractions. The uncertainty surrounding dark energy makes it challenging to predict which scenario will unfold, questioning the notion of eternity. Delving into cosmological epochs, the Stelliferous era, characterized by star formation from interstellar gas, will span 1 to 100 trillion years. Following this, the universe enters the degenerate era, marked by the cooling of white and brown dwarfs, neutron stars, and black holes. After around a duodecillion years, white dwarfs become black dwarfs, and brown dwarfs cool further. The black hole era ensues as black holes cluster or evaporate through Hawking radiation. This phase may last for 10 to the power of 100 years, resulting in vast expanses of space containing remnants like photons, electrons, positrons, neutrinos, and quarks. The universe could persist in this state indefinitely until the next significant cosmic event. The Sun's evolution is also explored, with Earth's habitability lasting another billion years before succumbing to the Sun's intensifying glow. Eventually, the Sun transforms into a white dwarf. However, predicting events after the universe's demise proves impossible, as the absence of time and space renders any conjecture meaningless. In conclusion, the journey through the universe reveals its intricacies, from multiverse theories to the uncertainties surrounding the universe's fate. Each cosmological era unfolds with distinct phenomena, providing glimpses into the vast and mysterious cosmos. While the ultimate destiny of the universe remains enigmatic, the exploration of its mysteries continues, promising ongoing educational revelations.